Look closely at a sunflower. Notice how its seeds spiral out from the center in a pattern so precise, so perfectly arranged. It seems almost too orderly to be natural. That pattern you're seeing isn't random, it's mathematical. It's the Fibonacci sequence, a numerical code found everywhere in the living world, from the curve of a nautilus shell to the branching of trees against the sky. For centuries, we've admired these designs as beautiful quirks of nature. But what if they're more than that? What if they're clues, an ancient, universal language written into the fabric of life itself? Now, as we stand on the brink of becoming an interplanetary species, engineers and scientists are beginning to listen to that language. They're asking a revolutionary question. Could the same patterns that shape life on Earth hold the key to surviving and thriving on other worlds? Imagine a future where habitats on Mars aren't built from scratch, but grown using algorithms inspired by forest networks. Where robots explore alien terrains not with rigid programming, but with the adaptive intelligence of a swarm. Where the deep code of cosmic design becomes our most powerful tool for engineering in environments we've never even seen. This is the story of how nature's math is reshaping our vision of the future. In this video, we'll journey from the spirals in our own backyards to the fractal edges of distant galaxies, exploring how bio-inspired engineering is turning science fiction into reality. We'll uncover how engineers are using principles from quantum biology, fractal geometry, and swarm intelligence to design technology that doesn't fight alien environments, but learns from them. So join us as we decode the universal blueprint hidden in plain sight, and discover how the oldest patterns in the universe may just hold the secret to humanity's future among the stars. This connection between the cosmic and the biological isn't a new idea. Over 2,000 years ago, the Greek philosopher Pythagoras proposed that the universe itself was a form of music, a harmony of the spheres where the movements of the planets created a kind of celestial symphony based on mathematical ratios. He believed numbers were the fundamental reality behind everything we perceive. Centuries later, the astronomer Johannes Kepler was so convinced of this musical, mathematical structure that he dedicated his life to finding it. And he did. His 3 laws of planetary motion describe the orbits of planets with an astonishing and precise mathematical elegance, proving that the clockwork of our solar system runs on a set of numerical rules. What's truly breathtaking is that these same rules seem to govern scales both unimaginably vast and incredibly small. Look up at a spiral galaxy like the Whirlpool Galaxy, and you'll see the same graceful logarithmic spiral you find in the shell of a chambered nautilus. This specific spiral shape, known for maintaining its form as it grows, is mathematically described by the golden ratio, a special number approximately equal to 1.618. This ratio, often denoted by the Greek letter phi, appears with an almost mysterious frequency. You can find it in the branching of your own bronchial tubes, the arrangement of seeds in that sunflower, and the proportions of some of the most enduring art and architecture in human history. As astrophysicist Mario Livio has explored, its prevalence suggests it represents a fundamental principle of efficient growth and structural stability, a kind of universal aesthetic. This points to something far deeper than mere coincidence. It suggests the existence of a deep code, an underlying set of instructions that the universe follows, whether it's assembling a galaxy, a weather system, or a living organism. A hurricane, for all its chaotic fury, organizes itself into a perfect logarithmic spiral. The branching pattern of a tree, which efficiently exposes its leaves to sunlight, is echoed in the branching pattern of a river delta, which efficiently moves water across a landscape. Even the way planets and moons orbit each other can fall into harmonic resonance, their orbital periods locking into simple whole number ratios, much like the harmonious intervals in a musical chord. So what does this mean for us as we look toward the stars? If the same mathematical patterns that sculpt alien worlds also shape the pine cone in your local park, then we already possess a kind of universal translator. This universal language of mathematics gives engineers a powerful starting point for designing technology for environments we cannot yet fully imagine. Instead of starting from zero, they can begin with nature's proven blueprints. Could the fractal branching of a lung inspire a more efficient system for distributing air and heat in a Martian habitat? Might the harmonic resonances that keep orbital systems stable inform the design of gravitational wave detectors or new methods of spacecraft propulsion? The patterns are all around us, waiting to be read. The question is, are we ready to listen to what the universe is trying to tell us? This universal mathematical language gives us a blueprint, but to turn that blueprint into working technology, engineers are turning to the most innovative laboratory we have, Earth itself. Our planet is a living catalogue of solutions, refined by billions of years of evolutionary trial and error in environments so extreme they rival the harsh conditions of alien worlds. The key is a practice called biomimicry, the art of innovating through imitation of nature's designs. Consider the humble gecko. This lizard can scamper up a perfectly smooth pane of glass, defying gravity with what seems like magic. The secret isn't glue or suction, but millions of microscopic hairs on its toes that exploit atomic-level forces. Engineers studying this biological marvel developed a revolutionary adhesive material. For space missions, this means astronauts could have grip pads on their suits and equipment, allowing them to work on the outside of a spacecraft or space station without the constant fear of tools, or themselves drifting off into the void. It's a simple, energy-free solution that outperforms any mechanical system we could invent. We can find another stunning example not in an animal, but in an insect's architecture. In the scorching deserts of Africa, termites build colossal mounds that tower over the landscape. Inside, despite external temperatures that can swing from blistering days to freezing nights, the termites maintain a constant, comfortable temperature to farm their fungus gardens. They achieve this not with air conditioning, but through a passive ventilation system of ingeniously placed tunnels and vents that channel breezes and release heat. Architects and engineers are now applying this precise design to buildings here on Earth, and the implications for Mars are profound. A Martian habitat must be thermally stable against a backdrop of extreme temperature fluctuations. By building with a termite's wisdom, we could create structures that regulate their own climate using the planet's natural atmospheric pressure and wind patterns, drastically reducing the energy needed for survival and making long-term colonization truly sustainable. These examples point to two powerful principles that nature has mastered and that are essential for operating in the unknown: adaptive structures and self-organizing systems. In biology, adaptability is everything. A tree bends in the wind rather than breaking. Its root system navigates around obstacles in the soil. This is the opposite of most human engineering, which values rigidity and permanence. For alien environments where conditions can change in an instant, we need technology that can respond. Imagine a solar panel array on Mars that could reorient its segments like leaves in a canopy to maximize light capture throughout the long Martian day, or a communications antenna that could reshape itself like a flower closing its petals to protect against an incoming dust storm. These aren't just futuristic concepts, they are active areas of research inspired by the flexible, resilient structures found all around us. self-organization is perhaps even more radical. An ant colony has no central command, no CEO ant directing traffic. Yet, through simple interactions between individuals following basic rules, the colony achieves complex goals like building intricate nests, finding the shortest path to food, and defending itself. This decentralized intelligence is incredibly robust. If you remove a few ants, the colony carries on. NASA is deeply interested in this kind of system for planetary exploration. Instead of sending one large, vulnerable rover, imagine sending a swarm of dozens of small, simple robots. Like a colony of ants, they could work together to map a vast cavern on Mars, build a structure, or collectively overcome an obstacle that would stop a single machine in its tracks. This approach, often called swarm robotics, offers redundancy and adaptability that a single, complex system cannot match. A brilliant case study in action comes from the world of aerodynamics. For decades, engineers designed aircraft and drones with fixed, rigid wings. But then they looked to the Hummingbird, a master of aerial agility that can hover, dart sideways, and even fly upside down. Its secret is wings that don't just flap, but twist and morph their shape with every movement, generating lift on both the upstroke and downstroke. By studying the precise fluid dynamics of this motion, researchers at NASA Ames Research Center developed a new type of drone wing. These bio-inspired wings are flexible and can change their shape in flight, granting drones a level of maneuverability and efficiency previously thought impossible. On a world like Titan, with its thick, soupy atmosphere, such agile flying machines would be the perfect tool for exploration, capable of navigating complex terrain with the grace and precision of a living creature. This entire approach is about shifting our mindset from one of conquest to one of collaboration. We are not trying to overpower alien environments with brute force technology shipped from Earth. We are learning to listen to the genius of our own planet, to borrow the strategies that life has already perfected for surviving and thriving against all odds. It's about working with the principles of nature, using local materials and energy flows to create technology that is not just placed on another world, but that truly belongs there. The efficiency of these biological solutions is their greatest strength. They show us how to do more with less, which is the ultimate requirement for any long-term future beyond our home planet. Picture a single bolt of lightning splitting the sky. In that brilliant, jagged flash, you're witnessing one of nature's most powerful examples of fractal geometry. The main trunk fractures into smaller branches, which then split into even smaller tributaries, all the way down to microscopic scales. This isn't a random explosion of energy, it's a pattern, a highly efficient one. The lightning bolt finds the path of least resistance through the atmosphere by exploring every possible route simultaneously across different scales. This same repeating, self-similar pattern is everywhere you care to look. It's in the intricate branching of a tree, the delicate structure of a snowflake, the sprawling network of a river delta, and even the way your own circulatory system distributes blood from your heart down to the tiniest capillaries. These are all fractals. The mathematician Benoit Mandelbrot gave us the language to describe these shapes that classical geometry, with its perfect smooth lines and circles, simply couldn't. He showed that fractals are how nature handles complexity and chaos, creating immense efficiency from stunningly simple rules. A fractal is a pattern that repeats itself at different scales, meaning you can zoom in on a tiny part of it and find the same structure you saw from far away. This isn't just an artistic curiosity, it's a fundamental principle of design for one critical reason. It maximizes surface area and optimizes distribution within a limited volume. Think of your lungs. If they were just two simple, smooth sacs, they would have a surface area roughly equal to your skin. But by branching into a fractal network of millions of tiny alveoli, they pack a surface area nearly the size of a tennis court into your chest. This incredible efficiency is what allows for the rapid exchange of oxygen and carbon dioxide that keeps you alive. Engineers are now harnessing this same principle to solve some of the most daunting challenges of space exploration. Consider the problem of a life support system on a spacecraft or a Martian base. It's a closed-loop environment where every gram of oxygen, every drop of water, and every nutrient must be meticulously managed and recycled. Distributing these resources efficiently is paramount. By using fractal algorithms to design the plumbing and air circulation networks, engineers can create systems that mimic the human circulatory system. These fractal pipelines would ensure that heat, air, and water are delivered evenly and effectively to every corner of a habitat, minimizing energy use and eliminating dead zones where carbon dioxide could build up or temperature could fluctuate dangerously. It's the difference between trying to water a large garden with a single hose and having an intricate capillary-level irrigation system built right into the soil. This application of fractal thinking extends far beyond pipes and vents. Look at the devices we use to communicate across the vastness of space. Traditional antennas often need to be large to operate at multiple frequencies, a serious problem when every cubic centimeter of a spacecraft's payload bay is precious. The solution came from, once again, looking at nature's blueprints. Fractal antennas incorporate those same repeating, self-similar patterns into their design. This allows a single, incredibly compact antenna to resonate at multiple frequencies efficiently, much like a fern frond is able to pack a massive amount of surface area into a small space. You'll now find these antennas in everything from smartphones to NASA satellites, making our connection to distant probes and rovers more reliable and far less bulky. Perhaps one of the most elegant applications is in managing the intense heat generated by electronic systems in the vacuum of space, where there's no air to carry it away. Engineers looked to the most effective cooling system they knew, the human body. Our blood vessels form a fractal network that brilliantly regulates temperature by bringing warm blood close to the skin's surface to cool it. Inspired by this, researchers have developed fractal-based heat exchangers. These devices use intricate, branching microchannels to circulate coolant, creating a massive surface area for heat transfer within a very small unit. This bio-inspired technology is being integrated into everything from high-powered spacecraft computers to the life support systems of next-generation spacesuits, keeping critical systems from overheating with an efficiency that rivals our own biology. This is the true power of the fractal concept. It provides a universal rulebook for building efficiency and resilience into our technology, whether we're designing for Earth or for the unknown environments of distant worlds. Now let's consider a seashell, specifically the chambered nautilus. As it grows, it adds new chambers in a precise spiral, each one perfectly proportioned to the last. This isn't just any spiral, it's a logarithmic spiral that expands by a factor of phi, the golden ratio, with each quarter turn. This same proportion, approximately 1.618 to 1, has captivated humans for millennia. It was used by ancient architects in the design of the Parthenon in Greece, a structure celebrated for its breathtaking visual harmony. The builders likely had no formal calculation of phi, but they intuitively understood that this specific relationship between width and height created a sense of balance and beauty that felt inherently right. This suggests that our attraction to this ratio might be more than a cultural preference. It could be woven into our very perception, a response to a pattern that nature itself uses repeatedly for stability and efficient growth. The intrigue deepens when we find this same number appearing in the cosmos. Astrophysicist Mario Livio, in his work on the subject, has explored how the golden ratio manifests in the physics of the universe. While not every spiral galaxy is a perfect golden spiral, many, like M74, exhibit this form with remarkable fidelity. Furthermore, the arrangement of planets and their orbital resonances can sometimes approximate these harmonic proportions. This isn't to say the solar system is a perfect musical instrument, but it hints that the same physical principles that govern gravitational dynamics might express themselves through these mathematically elegant patterns. It appears phi is more than just an aesthetic rule. It might be a natural consequence of efficient physical systems, whether they are building a shell, a galaxy, or a hurricane. This brings us to a fascinating frontier for engineering, applying the golden ratio to the design of habitats for other worlds. The challenge of living on Mars or the Moon isn't just about surviving radiation and extreme temperatures. It's about thriving in an environment that is profoundly alien and potentially stressful for the human psyche. Long-term confinement in a sterile, rectangular box could take a significant toll on crew mental health. What if the very proportions of the spaces we inhabit could help reduce that stress and improve functionality? This is where phi moves from an abstract concept to a practical tool. Engineers and architects are beginning to explore how rooms, doorways, and communal areas built to golden ratio proportions could create a subconscious sense of comfort and harmony for inhabitants. It's a form of ergonomic design that works on a psychological level, potentially making tight quarters feel more spacious and organized layouts feel more intuitive to navigate. The application extends to pure efficiency. Remember, nature uses phi because it works. In plant growth, arranging leaves or seeds at angles related to the golden ratio minimizes shadowing and maximizes sunlight exposure. For a greenhouse on Mars, arranging planting beds and light sources using these same principles could optimize growth and reduce energy costs. The spiral layout of a Nautilus shell is a masterclass in expanding living space efficiently. A habitat module that grows outward using a similar fractal spiral design could be modular and adaptable, allowing a base to expand logically over time without losing its structural integrity or its harmonious flow. This is cosmic aesthetics in action, beauty derived not from ornamentation, but from the inherent efficiency of the underlying mathematical form. This exploration inevitably leads to a profound, reflective question: is beauty in design truly universal? We are products of Earth's evolution, and our attraction to certain patterns, like the golden ratio, may be hardwired from seeing it in everything from the arrangement of our own facial features to the branching of trees. But would an intelligent species that evolved on a world with different gravitational forces, atmospheric pressures, and dominant biological forms find the same proportions pleasing? Or is our sense of aesthetic harmony a unique product of our planetary context? For engineers designing for international and increasingly interplanetary crews, this isn't just a philosophical debate. It has real implications. Should we design habitats based on a presumed universal standard of comfort and beauty, or must we create adjustable, customizable environments that can cater to a wide range of cultural and perhaps even species-specific preferences in the far future? The answer may determine whether a space station feels like a sterile machine or a true home, and that could be the key to humanity's long-term future among the stars. Walk into a dense forest and look up. The canopy above you is a chaotic tapestry of leaves and branches, but it's not random. Each tree is engaged in a silent, algorithmic dance, positioning its branches to capture the maximum amount of sunlight without overly shading its neighbors. This isn't a passive process. It's an active, growth-driven computation where simple rules grow toward light, branch at certain angles, result in an incredibly complex and efficient system for energy capture. Now picture that same principle applied on the red, dusty plains of Mars. Instead of trees, imagine fields of solar arrays that don't just sit statically on the ground, but that can slowly adjust their orientation and even their shape over time, reorganizing themselves like a forest canopy to optimize energy absorption throughout the long Martian seasons. This is the promise of algorithmic growth, a field where engineers are learning to code matter itself to behave like a living thing. The mathematical key to unlocking this potential is called an L system, or Lindenmayer system. Developed in the 1960s by the Hungarian biologist Aristid Lindenmayer, it wasn't originally meant for engineering at all. Lindenmayer was trying to find a formal way to describe the simple, recursive growth patterns of algae and fungi. He created a grammar, a set of symbolic rules where a single starting string of letters is progressively rewritten according to production rules. For example, a rule might say, replace every letter F with F plus left bracket plus F plus right bracket minus F. When this rewriting process is interpreted graphically with F meaning, draw a line forward, and the brackets controlling branching angles, these simple instructions can generate stunningly realistic models of trees, bushes, and ferns. This made L systems a revolutionary tool in computer graphics, used to create entire digital forests in animated films. But engineers soon realized its power went far beyond creating pretty pictures. It provided a blueprint for building physical objects that could grow and adapt. The true genius of L systems lies in how they mirror the process of evolution itself. In nature, an organism's form is dictated by its genetic code, which is essentially a set of instructions executed in response to environmental cues. A computational biologist would point out that an oak tree and a pine tree look different not because they have entirely different biological hardware, but because they run different software, slightly variations in their genetic algorithms. L systems give engineers a way to write and execute similar software for non-living materials. This opens the door to what's known as procedural generation, where a complex, optimized structure isn't designed in every minute detail by a human engineer, but is instead generated by an algorithm that can respond to specific, changing conditions. One of the most transformative applications of this is in advanced manufacturing, particularly for space habitats. Imagine a large 3D printer sent ahead to Mars. Instead of printing a rigid, pre-designed habitat that might not be perfectly suited to its actual landing site, it uses an L system-based algorithm. The printer begins with a core seed structure, and its growth instructions are influenced by real-time sensor data. If it encounters a particularly hard layer of rock on one side, the algorithm adjusts, growing the foundation around it for stability, much like a root navigates around a stone. If sensors detect that one area will receive more sunlight, the algorithm might generate a branching network of support pillars that double as light channels, optimizing the internal environment. The final structure isn't a static box. It's an organically grown, site-specific home that is inherently stronger and more efficient because its form was computed in real time to fit its environment. This principle of responsive, algorithmic growth isn't limited to stationary habitats. NASA Jet Propulsion Laboratory has experimented with prototype robots that move through unpredictable terrain using what's known as a route-like exploration strategy. A traditional rover plans a single, optimal path from point A to point B, but on a world with loose sand, sharp rocks, and steep inclines, that path can easily become blocked. A bio-inspired robot, however, would operate on a much simpler set of L system-like rules. Extend a limb if you encounter resistance, retract and branch out in a different direction, always seeking the path of least resistance. Multiple small robots could work as a decentralized network, their collective growth and exploration mimicking a root system spreading through soil, efficiently mapping and navigating caves or lava tubes on other worlds that would be far too risky for a conventional, centrally controlled vehicle. This shift in philosophy from pre-planned rigidity to adaptive, algorithmic growth could ultimately be what allows us to tame the most unpredictable and alien landscapes in our solar system. Watch a single ant scrambling across the ground and it might seem aimless, even chaotic, but step back and observe the colony as a whole and you witness something extraordinary, a sophisticated city-building society with no architect, no foreman, and no central command. Thousands of individuals, each following a simple set of instinctive rules, work together to construct intricate underground nests, forage for food across vast distances, and defend their home with stunning coordination. They achieve this not through top-down orders, but through a constant stream of local interactions touching antennae, leaving chemical trails, and responding to the work of their neighbors. This emergent intelligence, known as swarm intelligence, is one of nature's most powerful strategies for solving complex problems in unpredictable environments. And it's providing a radical new blueprint for how we might explore worlds millions of miles away. The core principle here is decentralization. In a traditional mission, a single, multi-million-dollar rover like Perseverance is an engineering marvel, but it's also a single point of failure. If it gets stuck in sand or a critical system fails, the entire mission can be jeopardized. Swarm robotics flips this model entirely. Instead of one complex machine, imagine sending a fleet of dozens or even hundreds of small, simple, and relatively inexpensive robots to Mars. Individually, each unit is limited, but collectively, like an ant colony, they become something far greater than the sum of their parts. They gain the advantages of redundancy. If a few units break, the mission continues, and of adaptability, as the swarm can fluidly reshape itself to overcome obstacles no single robot could handle. As one engineer at NASA Jet Propulsion Laboratory put it, a swarm allows you to be in many places at once, to take on multiple tasks simultaneously, and to take risks we could never afford with a flagship asset. The magic that makes this possible is a class of algorithms inspired directly by the behavior of social insects, birds, and fish. One of the most influential is called particle swarm optimization. Picture a flock of birds searching for a food source in a large forest. No one bird knows where the food is, but each bird shares information with its neighbors about the best area it has personally found. Gradually, through this simple communication, the entire flock converges on the optimal location. Computer scientists have translated this behavior into a powerful algorithmic tool. For a swarm of rovers tasked with mapping the volatile terrain of a lava tube on Mars, particle swarm optimization would allow them to work together without a central map. Each rover would explore its immediate vicinity, sharing data on the most interesting geological features or the safest paths it has discovered. The entire network would then collectively decide how to redeploy itself to cover the most ground efficiently, building a detailed, shared map of the unknown environment in real time. This approach is already moving from theory to practice in laboratories and testing grounds around the world. The European Space Agency has studied the Sonar project, which envisions a swarm of small, ball-like robots called Sphere X that could hop and roll across the low-gravity terrain of an asteroid, working together to create a detailed 3D model of its surface. Back on Earth, researchers are testing swarms of drones that can collaboratively construct simple structures or survey disaster zones, demonstrating the core principles of decentralized coordination. The key to these systems is that the intelligence is embedded in the connections between the robots, not in a single, powerful brain. This bio-inspired coordination drastically reduces the need for constant micromanagement from mission control on Earth, where a one-way communication delay to Mars can be 20 minutes or more. The swarm can simply be given a high-level goal, map this crater, or assemble this solar array, and it will figure out the most efficient way to achieve it on its own. This incredible autonomy, however, brings with it a profound ethical dimension that we must confront. As we design systems capable of making their own decisions and acting on them without direct human input, where do we draw the line? We are comfortable with a swarm of robots deciding the best path up a hill, but what if the best path involves a calculated risk to one of its members? Should a robotic collective be allowed to sacrifice a unit for the greater good of the mission? And who is ultimately responsible for the actions of a decentralized, self-organizing system, the programmer who wrote the initial algorithms, the engineer who launched them, or the agency that funded the project? These are not questions for distant science fiction. They are practical design considerations for the next generation of planetary exploration. The answers will shape not only the success of our missions, but the very principles we carry with us as we extend our presence into the cosmos. For billions of years, life on Earth has been performing what we would call quantum miracles, manipulating the subatomic realm with a mastery that our finest laboratories are only beginning to comprehend. Long before we had equations for superposition or entanglement, a migrating robin was leveraging the bizarre laws of quantum mechanics to navigate across continents, and a simple leaf was conducting a form of quantum computation to turn sunlight into food. This isn't science fiction, it's the cutting-edge field of quantum biology, and it reveals that nature is the original quantum engineer. As we venture into the cosmos, into environments with faint sunlight, weak magnetic fields, and intense radiation, this ancient quantum wisdom may hold the key to technologies that seem like magic by today's standards. At the heart of this mystery are phenomena that defy our classical, everyday intuition. Take quantum coherence, for instance. In our macroscopic world, things have a definite state and location. But in the quantum realm, a particle like an electron can exist in multiple states at once, a principle called superposition. It can also tunnel through an energy barrier that, according to classical physics, should be completely impassable. For decades, we assumed these fragile effects could only be observed in the sterile, ultra-cold vacuum of a physics lab. Then, biologists made an astonishing discovery. Inside the photosynthetic complexes of plants and bacteria, photons of sunlight are absorbed, and their energy is converted into excitons, effectively packets of energy. Researchers found that these excitons don't just bump around randomly like pinballs to find the reaction center where they're converted into chemical energy. Instead, they exploit quantum coherence. They act like waves, exploring all possible pathways through the photosynthetic system simultaneously, instantly and efficiently finding the most optimal route. This quantum effect allows the process to be nearly 100% efficient, a benchmark our best human-made solar cells can only dream of approaching. This revelation opens a breathtaking avenue for engineering on worlds far from the Sun. Imagine a future outpost on Pluto where sunlight is 1,000 times dimmer than on Earth, or in the perpetual twilight of a distant asteroid. Standard photovoltaic panels would be nearly useless, but what if we could create quantum-inspired solar cells that operate like a leaf, by designing materials that can maintain quantum coherence at room temperature, or better yet, at the cryogenic temperatures of deep space, we could develop energy harvesters of incredible sensitivity. These devices wouldn't just passively absorb light. They would use quantum tricks to funnel every precious photon of energy directly to where it's needed, turning even the faintest starlight into a viable power source. This isn't merely an improvement on existing technology. It's a fundamental leap, learning to work with the quantum grain of the universe rather than against it. The quantum connection extends beyond energy to the very challenge of navigation in the featureless void. Here on Earth, birds like the European robin perform annual migrations over thousands of miles, guided by the planet's magnetic field. For years, we assumed they had some kind of microscopic compass needle in their heads. The truth is far more strange and wonderful. Evidence now strongly suggests that a quantum effect is at play within a protein in the bird's retina called cryptochrome. When a photon of light strikes this protein, it creates a pair of molecules with electrons that become quantumly entangled. Their spin state is exquisitely sensitive to the angle and strength of the Earth's magnetic field. The bird doesn't see the field as we might see a compass dial. It literally perceives it as a visual pattern overlaying its sight, a kind of quantum heads-up display that points the way south. This is nature's GPS, and it operates without satellites, without batteries, using only the fundamental weirdness of quantum mechanics. For space exploration, this biological insight is revolutionary. Many worlds we aim to explore, like Mars or the Moon, have only patchy or extremely weak magnetic fields. Our traditional navigational systems rely on satellites or beacons, infrastructure that doesn't exist beyond Earth. A spacecraft entering orbit around a moon like Callisto, or a rover traversing the dusty plains of a world with no global magnetic field, could easily become disoriented. By reverse engineering the avian quantum compass, we could develop a new generation of ultra-sensitive magnetometers. These sensors would allow probes and rovers to orient themselves using the faintest magnetic whispers of a planet's crust or the subtle pull of the solar magnetic field, providing a fail-safe navigation system that works anywhere, completely independent of human input. It would be like giving our machines a true sense of direction, an innate feeling for where they are in space that is borrowed directly from the animal kingdom. Perhaps the most immediate application lies in the urgent problem of radiation shielding. On Earth, we are protected from the full fury of cosmic and solar radiation by our atmosphere and magnetic field. Beyond this cocoon, astronauts and electronics are bombarded by high-energy particles that can damage DNA and fry delicate circuits. While we currently rely on thick, heavy shielding, a major constraint for spacecraft design, nature might offer a more elegant solution. The bacterium Deinococcus radiodurans can survive radiation doses thousands of times what would kill a human. It does this through incredibly efficient DNA repair mechanisms, but some scientists speculate that quantum tunneling might play a role in how these repair proteins locate and fix damage so quickly. Furthermore, the melanin in our own skin, which protects against ultraviolet radiation, has been shown to have interesting quantum electronic properties. Could we engineer a material that doesn't just passively block radiation, but actively manages it? A smart shield that uses quantum principles to dissipate harmful energy or even convert it into a harmless form. Such a material would be lightweight, multifunctional, and transformative for human deep space travel, turning a major obstacle into a manageable engineering parameter. All of this forces us to confront a profound question about the laws of physics themselves. For centuries, classical Newtonian physics has been more than sufficient to describe the world we experience directly. It got us to the moon, but as we push into the extreme and alien environments of the cosmos, are we approaching the limits of this classical worldview? The bizarre, counterintuitive rules of quantum mechanics aren't just a novelty, they appear to be the operating system of the universe on the smallest scales. Life on Earth has been running on this software for eons. If we hope to build technology that can not just survive but thrive on other worlds, we may need to stop thinking like classical engineers and start thinking like quantum biologists, learning to design with the strange and spooky laws that truly govern the fabric of reality. Beneath the sun-drenched waves of a tropical ocean, a coral reef thrives in a world of constant change. It faces the relentless pounding of hurricane-force waves, the sudden shifts in temperature, and the occasional invasion of predatory species. Yet it endures not through sheer, unyielding strength, but through a brilliant strategy of diversity and built-in backups. A reef is not one single, massive structure. It's a sprawling metropolis of countless different corals, each species with a slightly different shape, density, and growth pattern. When a storm smashes through, the more fragile, branching corals might break away, but the sturdy, boulder-like brain corals remain, providing the foundation for the entire community to regenerate. This inherent variety is the reef's secret weapon, a form of biological redundancy that ensures no single event can deliver a knockout blow. It's a powerful lesson from Earth's ecosystems, and one that stands in stark contrast to much of our historical approach to engineering for space, where we have often placed our bets on singular, monolithic, and incredibly complex systems that represent a single point of catastrophic failure. This principle of resilience through redundancy is fundamental to how life itself persists. An ecosystem doesn't put all its energy into one superspecies, it fills countless niches. If a drought wipes out one type of grass, another with deeper roots may survive. This biological wisdom is now critically informing a new philosophy for designing technology destined for alien worlds, where the unknowns are vast and the consequences of failure are absolute. As one systems engineer at the Jet Propulsion Laboratory often explains, redundancy isn't about waste or duplication. It's about acknowledging the limits of our foresight. For a mission that takes a decade to plan and years to reach its destination, you can't possibly anticipate every rock, every storm, every software glitch. You build in backups so that the system can handle surprises you never even imagined. This mindset shifts the design goal from creating a perfect, infallible machine to creating a resilient, adaptable one that can gracefully degrade and continue its mission even when things go wrong. We can see this principle in action at its most basic level in the architecture of the International Space Station. The station's electrical system is a masterclass in layered redundancy. It doesn't rely on one single power source. It has multiple massive solar arrays, each capable of picking up the slack for another. Its internal systems are routed through a complex network of switches and converters, allowing power to be rerouted along dozens of different pathways if one line is damaged. The life support system has backups for its backups. If the primary oxygen generator fails, there are tanks of stored oxygen and even solid fuel canisters that can produce breathable air in a final emergency. This isn't over-engineering, it's a direct application of the lesson from the coral reef. By distributing critical functions across multiple, independent components, the station ensures that a single meteoroid puncture or a failed pump doesn't spell disaster for the entire crew. Taking this concept further, engineers are looking to nature for even more sophisticated models of resilience. Consider the modular design of our own bodies, inspired by cellular structures. Your body is composed of trillions of cells. If you skin your knee, you don't shut down. A localized team of cells springs into action to repair the damage while the rest of your body continues to function normally. This is the inspiration for a new generation of modular spacecraft and planetary habitats. Instead of one large, pressurized vessel, imagine a base on Mars constructed from dozens of interconnected, smaller modules. If a decompression event occurred in one module due to a micrometeoroid strike or structural fatigue, that single compartment could be sealed off and isolated. The crew would lose a room, but not their lives or the entire habitat. The rest of the base would remain operational, buying precious time for repairs. This cellular approach fundamentally changes the safety equation, moving from a prevention-only model to one that also incorporates graceful containment and recovery. The need for this kind of thinking is underscored by painful lessons from history. The loss of the Space Shuttle Columbia in 2003 is a tragic case study in the perils of a single point of failure. The investigation revealed that the cause was a piece of foam insulation that broke off during launch and struck the leading edge of the shuttle's wing, damaging the thermal protection system. Upon re-entry, superheated plasma penetrated the wing and led to the destruction of the orbiter. The system lacked a redundant solution. There was no backup heat shield, no way for the crew to inspect and repair that specific type of damage, and no escape pod. The failure of one small component in one critical location led to the loss of the entire vehicle and its crew. This event forced a profound rethink in aerospace engineering, leading to much more rigorous analyses of potential failure modes and a much greater emphasis on designing systems that can either withstand the loss of a component or provide an alternative pathway for completing a mission. This evolution in design philosophy points toward creating truly fault-tolerant networks, much like the neural systems in advanced animals. Your brain has an incredible ability to reroute information around damaged areas. While a severe injury can cause impairment, many functions can be gradually recovered as new neural pathways are formed. Engineers are working to imbue spacecraft and planetary infrastructure with a similar kind of resilience. This involves creating distributed computing systems where critical calculations aren't performed in one central computer, but are shared across a network of processors. If one fails, its tasks are automatically redistributed to the others. It means designing communication networks with multiple, redundant data paths, so that if a primary antenna fails, a secondary system on another part of the ship can take over, perhaps using a different frequency or protocol. The goal is to create a technological immune system, a network that can sense a failure, isolate it, and adapt its operations to work around the problem, ensuring that the mission's core objectives can still be achieved even in a degraded state. Ultimately, this shift is about more than just adding extra parts. It's about a fundamental change in how we approach the unknown. We are moving from a paradigm of prediction and prevention to one of absorption and adaptation. We may not know what specific threats a habitat on the icy surface of Europa will face, perhaps it's ice quakes, radiation spikes, or something we haven't even conceived of. But by designing that habitat like a coral reef or a neural network, with built-in diversity, distributed function, and multiple layers of backups, we can create systems that are inherently robust. They become antifragile, gaining from disorder, able to withstand the unpredictable chaos of an alien environment, not because we predicted every possible failure, but because we designed them to learn from failure and evolve right along with the challenges they encounter. Stand in the heart of an old-growth forest and you are surrounded by the ultimate model of efficiency. Fallen leaves decompose into rich humus, feeding the trees that cast the shade. Those trees transpire water vapor, contributing to the local rainfall that nourishes the entire system. A fallen log isn't waste, it's a nursery for new saplings and a habitat for countless insects. In this ecosystem, there is no landfill, no concept of garbage. Every output from one process becomes a valuable input for another in a beautifully closed, continuous loop of energy and matter. This stands in stark contrast to the linear systems that dominate our modern world on Earth, where we extract resources, use them once, and then discard them as waste, a take, make, dispose model that is fundamentally unsustainable, especially for a future among the stars. This contrast highlights a revolutionary shift in engineering philosophy, moving from a linear to a circular economy. As Dr. Lynn Rothschild, an astrobiologist and synthetic biologist at NASA Ames Research Center, often emphasizes, nature doesn't do waste. Every molecule is currency and every byproduct is an opportunity. For long-term space habitation, we have to think the same way. We can't afford to throw anything away. This is the core of biomimicry in energy design, not just copying a single shape or material, but emulating the deep, systemic logic of natural cycles. The goal is to create closed-loop life support systems that function like miniature planets, recycling air, water, and nutrients with near-perfect efficiency, turning a Mars base or a lunar outpost from a vulnerable lifeboat into a self-sustaining ark. The most critical and well-developed application of this principle is in bio-regenerative life support. The challenge is profound. How do you provide a crew with breathable air, drinkable water, and nutritious food for years without constant, astronomically expensive resupply missions from Earth? The answer is being developed in laboratories that look more like futuristic greenhouses. Scientists are cultivating specific strains of algae, such as spirulina, in large photobioreactors. These microscopic plants are powerhouses of photosynthesis. As they grow, they consume the carbon dioxide exhaled by astronauts and, using energy from specially tuned LEDs, convert it into fresh oxygen. But the magic doesn't stop there. The algae itself is a protein-rich biomass that can be harvested and eaten, or used as a fertilizer to grow other crops in hydroponic systems. Even the water they are grown in can be purified and recycled. This creates a beautiful, symbiotic loop between human and plant, mirroring the relationship between animals and plants on Earth. This isn't just theoretical. The European Space Agency's ME-LI-SSA program, which stands for Microecological Life Support System Alternative, is one of the most ambitious projects bringing this vision to life. ME-LI-SSA is essentially an artificial ecosystem in a can, a complex closed-loop system that uses a series of interconnected compartments to break down waste and regenerate resources. One compartment contains bacteria that break down solid human waste. Another uses photosynthetic bacteria to further process those breakdown products. The next features plants and algae that produce oxygen and food, all working in concert to create a sustainable cycle. Research from ME-LI-SSA is already finding applications on Earth in areas like wastewater treatment and air purification, proving that the solutions for living in space can also help us live more sustainably on our home planet. Beyond the life-giving cycles of air and water, the principle of energy efficiency extends to the very design of the habitats themselves. Here, engineers are once again turning to the genius of natural architecture, such as the termite mounds we discussed earlier. These structures use passive ventilation, harnessing natural pressure gradients and wind to circulate air and regulate temperature without consuming a single watt of energy. For a base on Mars where energy is a precious commodity, this passive approach is invaluable. Architects are designing habitats with similar wind-catching towers and strategically placed vents that use the planet's own thin atmosphere and daily temperature swings to create convection currents, passively circulating air and cooling living spaces. drastically reducing the load on mechanical life support systems. The concept of harvesting energy from environmental gradients is another frontier inspired by nature's thriftiness. On Earth, many organisms have evolved to exploit tiny differences in their environment. The Atlantic razor clam, for instance, can burrow deep into the seabed using minimal energy by cleverly manipulating the soil around it into a liquid-like state. Engineers are looking at how to harness similar gradients on other worlds. The most promising is the temperature gradient, the difference between the sun-soaked surface of a moon and the frigid cold just a few feet underground, or the swing between day and night temperatures, represents a vast, untapped source of energy. By using materials that undergo a phase change like waxes that melt and solidify, or through thermoelectric devices that generate electricity directly from a heat difference, we could create systems that passively harvest energy simply from an environment's natural cycles, powering sensors or small instruments indefinitely without the need for solar panels or nuclear batteries. All of these innovations point toward a future where human presence in space is not a constant, fragile battle against the environment, but a harmonious integration with it. It forces us to reflect on a larger question. If we can design such elegant, closed-loop systems for Mars, why are we so slow to implement them on Earth? Our reliance on fossil fuels is the epitome of the linear model, extracting ancient sunlight stored underground, burning it once, and releasing the waste products into our atmosphere with devastating consequences. The technologies being pioneered for space exploration, from algal bioreactors to passive cooling and gradient harvesting, offer a blueprint for a new industrial revolution on our own planet. They show us that true energy efficiency isn't about finding more powerful fuels, but about learning to do more with less, about creating systems where waste is an obsolete concept, and every joule of energy is made to work in a continuous, sustainable cycle, just as nature has done for billions of years. Picture a future habitat nestled on the surface of Titan, Saturn's largest moon, where the air is a thick, frigid soup of nitrogen and methane, and the temperature hovers around -290 degrees Fahrenheit. Suddenly, a dramatic temperature swing occurs, a common event on this turbulent world. Instead of the habitat's outer shell straining and cracking under the stress, it responds almost organically. Its insulation thickens and becomes more porous, trapping more heat inside as the exterior grows colder. Then, as a brief, weak sunbreak warms the surface, the material subtly thins, venting excess heat to prevent overheating. This isn't a crew manually adjusting a thermostat. It's the habitat's very skin, an adaptive smart material, responding to its environment with the same instinctive intelligence as a pine cone opening its scales in dry air or an octopus seamlessly blending into a coral reef. This is the next frontier of cosmic engineering, not building static structures but growing dynamic, shape-shifting systems that feel and react to their world. These smart materials represent a profound shift in our approach, one born directly from biomimicry. For decades, materials science focused on creating substances with fixed, reliable properties, strong alloys, durable ceramics, stable polymers. But nature rarely operates with such rigidity. As a materials scientist at MIT might explain, biology is the master of dynamic response. A pine cone doesn't have a sensor and a motor. Its structure is its sensor and its motor. The cellulose fibers in its scales are arranged at precise angles so that changes in humidity cause them to swell or shrink, forcing the scale to open or close. That's a material that computes its environment and acts on it, all without a single microchip. This principle of building intelligence directly into the material's microstructure, rather than bolting it on with electronics, is the revolutionary core of this field. It leads to systems that are far more robust, energy efficient, and adaptable, exactly what we need for environments where repair is impossible and failure is not an option. One of the most transformative applications of this idea is in the development of self-healing composites for spacecraft hulls. The vacuum of space is a brutal environment, filled with micrometeoroids tiny as dust grains yet traveling at velocities faster than a bullet. An impact, even a minuscule one, can create a hairline crack in a spacecraft's skin. Left unchecked, that crack can propagate under stress, potentially leading to a catastrophic decompression. Inspired by the human body's ability to clot blood and repair skin, researchers have created composite materials embedded with microscopic capsules of liquid healing agent. When a crack forms, these capsules rupture, releasing the agent into the damaged area. Upon contact with a catalyst woven into the composite, the agent hardens, effectively gluing the crack shut and restoring most of the material's original strength. This isn't a far-off concept. It's already being tested for use in satellite components and is a leading candidate for the outer shells of long-duration interplanetary vessels, offering a level of resilience that was once the domain of science fiction. Beyond healing, adaptive materials are being engineered for proactive protection. Consider the challenge of radiation on a journey to Mars or a base on the Moon. Current shielding is heavy and passive, but what if a material could change its properties to better deflect or absorb radiation only when it was needed? This is the goal of research into color-changing and phase-shifting coatings. One project, drawing inspiration from cephalopods like the octopus and cuttlefish, is developing polymers that can alter their electronic structure and thus their color and density in response to an electrical stimulus or even the radiation itself. A hull coating could remain light and transparent during periods of low radiation, but upon sensing a solar storm, it could darken and become denser, effectively turning into a more protective barrier. This on-demand shielding would drastically reduce the mass of a spacecraft over a mission's lifetime, as you wouldn't need to carry a full shield for every moment, only the potential for one. The quest for comfort and efficiency in harsh environments also leads us to textiles. The next generation of spacesuits won't just be passive garments, they will be active, responsive systems. Scientists are looking to the animal kingdom, to the way a polar bear's fur traps insulating air or how a rabbit's fur can lie flat or stand on end to regulate heat loss. Advanced smart fabrics are now in development using shape memory polymers and microfluidic channels. Imagine a glove that, when it senses the cold of the lunar night, automatically tightens its weave to reduce heat loss, or a boot that stiffens to provide support during high-impact activity on an asteroid and softens for comfort during long periods of station keeping. These textiles would act as a second skin for astronauts, dynamically managing their microenvironment to reduce energy expenditure on heating and cooling, and greatly enhancing their safety and comfort. This movement toward autonomy in materials, however, brings with it a host of profound ethical questions we are only beginning to confront. As these substances become more complex and lifelike, where do we draw the line between a smart material and a living machine? If a habitat's wall can sense, react, and even heal itself, does it possess a form of primitive agency? And who bears responsibility when an autonomous material makes a decision with unintended consequences? If a radiation shielding coating fails to activate properly during a solar flare, is the fault with the engineer who designed the polymer, the programmer who coded its response threshold, or the material itself? These are not abstract puzzles. They are pressing design considerations that will shape the safety protocols and legal frameworks for the next era of exploration. The power of materials that act on their own accord is immense, but it demands a parallel evolution in our thinking about control, risk, and the very nature of the tools we build to survive among the stars. Consider the stark difference between an astronaut returning from 6 months on the International Space Station and a deep-diving elephant seal. The astronaut, despite a rigorous exercise regimen, has lost significant bone density and muscle mass, their body having adapted to the energy-saving logic of microgravity by shedding what it deemed unnecessary. The elephant seal, on the other hand, routinely plunges to crushing depths, its bones and physiology reinforced to handle immense pressure, a form of high-gravity environment. This is nature's brilliant, real-time demonstration of structural optimization in response to mechanical load. It's a principle that engineers are now urgently applying through a revolutionary design process called topology optimization, ensuring our habitats and machines are not just built for other worlds, but are truly shaped by them. Topology optimization is, at its core, a form of computational evolution. It's a mathematical method that allows engineers to input a set of constraints like the force of gravity on Mars, which is about 38% of Earth's, or the load a lunar landing leg must support, and then ask a simple, profound question. What is the absolute most efficient way to distribute material within a given space to meet these requirements? The algorithm then works iteratively, much like bone cells called osteoblasts and osteoclasts that constantly remodel our skeletons in response to stress. It starts with a solid block of virtual material and strategically removes bits that aren't carrying significant load, leaving behind an intricate, organic-looking structure that is simultaneously incredibly strong and astonishingly light. The resulting forms often look less like human-designed trusses and more like the inside of a bird's bone or the branching structure of a tree patterns perfected by evolution for maximum strength with minimum weight. This bio-inspired digital forging is perfectly suited for the extreme constraints of space travel, where every kilogram launched from Earth costs a fortune in fuel and money. Instead of designing a bracket or a mounting plate as a simple, solid piece of metal, engineers use topology optimization to create complex, web-like lattices that perform the same function using a fraction of the material. The most exciting application of this is in additive manufacturing, or 3D printing. Companies like SpaceX are already using this combination of algorithmic design and 3D printing to create critical components for their rocket engines, resulting in parts that are stronger and lighter than those made with traditional methods. For lunar bases, this technology is nothing short of transformative. Imagine a large 3D printer using regolith, the dusty soil on the moon's surface, as its feedstock. Guided by topology optimization algorithms tuned for the moon's 1/6 gravity, it could print entire habitat walls or structural supports that are not just shelters, but highly engineered artifacts. There forms a direct conversation between mathematical logic and the local gravitational environment. This leads us to a fascinating long-term consideration that blends engineering with speculative biology. If topology optimization can shape our habitats, what will prolonged exposure to low gravity do to the shape of us? We already see the human body's remarkable plasticity in the muscle atrophy and bone loss experienced by astronauts. Over generations, could human settlers on Mars evolve a different physiological topology? Would their skeletons, no longer needing to resist Earth's full pull, become more delicate, their musculature lighter? This isn't just science fiction, it's a question of adaptive pressure. Our engineering mirrors this potential biological future. We are already designing for the human body as it is today, creating chairs, tools, and layouts that work in partial gravity. But the ultimate design project might be far more profound. not just designing structures for humans, but eventually designing the human form itself through natural selection or even deliberate genetic engineering to optimally fit the worlds we wish to call home. Deep in the crushing blackness of the ocean's abyss, where sunlight dares not penetrate, life thrives in a world of sound and sensation. Here, the Pacific black dragonfish navigates the eternal night not with eyes that see light, but with a lateral line system that feels the subtlest disturbances in the water pressure, and with photophores on its body that create its own faint glimmers to communicate. It is a master of a reality beyond our own visual perception, a living testament to the fact that our five senses are not a universal standard, but merely one evolutionary solution to understanding the world. This profound truth is the key to unlocking the exploration of alien environments, like the subsurface ocean believed to churn beneath the icy crust of Jupiter's moon, Europa. In such a place where light may not exist and magnetic fields could be strange or absent, our human-designed sensors would be nearly blind. The solution, then, is not to try and force our sensory model onto these worlds, but to learn from Earth's own experts in the extraordinary, to build machines that can see with sound, taste the air, and feel magnetic fields, just as the animals of our planet have done for eons. This endeavor is at the heart of a field called bio-inspired sensing, a discipline that sits at the crossroads of robotics, biology, and materials science. A roboticist working at NASA, a jet propulsion laboratory, might explain it like this. We are, in a sense, giving our robots new senses. We're not just building better cameras, we're building entirely new organs of perception based on biological blueprints that have been field-tested for millions of years. This approach moves beyond simply making more sensitive versions of our own instruments. It involves decoding the underlying biological principles, the specific proteins, cellular structures, and neural processing methods that allow a shark to detect the minute electrical fields of prey buried in sand, or allow a platypus to sense the muscular contractions of a shrimp with its bill while its eyes and ears are closed. By reverse engineering these capabilities, we can create technology that operates on a fundamentally different level, capable of interpreting environments that would otherwise be incomprehensible to us. One of the most advanced areas of this research involves sophisticated sonar systems inspired by the aquatic masters of sound. Dolphins don't just use echolocation to avoid obstacles. They use a complex repertoire of clicks and whistles to identify the size, shape, density, and even internal structure of objects. They can distinguish between a rock and a fish-filled canister from a remarkable distance, all by interpreting the returning echoes. Engineers are now developing biomimetic sonar for underwater drones or for potential submersibles destined for Europa's ocean. These systems don't just send out a single ping and measure the return time. They use arrays of transmitters and receivers to create a rich, three-dimensional sound picture of the environment, capable of identifying the texture of an icy wall, the composition of a hydrothermal vent chimney, or the unique acoustic signature of potentially interesting geological formations. This would allow a robotic explorer to see its surroundings in stunning detail through the medium of sound, just as a dolphin does, turning a pitch-black alien sea into a mapped and navigable space. Beyond sound, the chemical landscape of an alien world holds a wealth of information, if only we have the right tools to read it. Here on Earth, the humble moth possesses antennae that are miracles of chemical engineering. They are covered in thousands of microscopic pores and sensilla that can detect a single pheromone molecule from a potential mate over a kilometer away. This isn't a blunt instrument, it's an exquisitely tuned and highly specific sensor. Mimicking this capability is a major goal for astrobiology, A rover on Mars, for instance, could be equipped with an electronic nose based on moth antennae. Instead of digging for specific samples, it could simply taste the thin Martian air, detecting the faintest traces of complex organic molecules that might be signs of past or present life. This bio-inspired sensor would be millions of times more sensitive than current spectrometers, capable of sniffing out biosignatures that would otherwise be completely missed, guiding the rover to the most promising sites for further investigation without any human direction. Perhaps the most mysterious and compelling bio-inspired sense is magnetoception, the ability to perceive the Earth's magnetic field. For migratory birds like the Arctic tern, which travels from pole to pole, this sense is an internal compass more reliable than any human-made instrument. As we discussed earlier, evidence suggests this may involve a quantum biological process within the bird's eyes. For exploring worlds with weak or irregular magnetic fields, like Mars or some asteroids, this biological principle is invaluable. Engineers are developing solid-state magnetometers that mimic the suspected quantum coherent mechanism in bird cryptochrome proteins. These sensors would be incredibly sensitive to the faintest magnetic anomalies, allowing a rover to map the magnetic history of Martian rocks to understand the planet's past, or to navigate across the featureless plains of an asteroid by sensing the subtle variations in its magnetic crust, creating a map where no visual landmarks exist. The tangible potential of these ideas is already being tested in some of the world's most advanced laboratories. At JPL, researchers have developed a rover concept called the Bio-Inspired Autonomous Rover for non-terrestrial environments. This isn't a single machine with one primary camera system. It's a platform designed to integrate multiple bio-inspired sensors, allowing it to perceive its world in a layered, multi-modal way, much like an animal. It might use whisker-like probes to feel the texture and stability of soil, an electronic nose to analyze soil vapors, and sensitive microphones to listen for the subsurface sounds of shifting geology. This approach creates a robust and redundant perception system. If one sensor is blinded by dust or darkness, the others can take over, building a composite picture of the environment that is far richer and more reliable than any single sense could provide. All of this technological marvelry leads us to a deeply philosophical and personal question about our own place in the universe. For all of human history, our understanding of reality has been filtered through the narrow window of our own senses. We have built tools like telescopes and microscopes to extend the reach of those senses, but they have largely remained interpretations of the world as we experience it. Bio-inspired sensing represents something radically different. It is the first step toward building tools that experience the world in a fundamentally alien way, that can hear magnetic fields, see with chemical gradients, and feel the quantum vibrations of the universe. These technologies will not just tell us what is on another planet, they will, in a very real sense, tell us what it is like to be there. They are our first true interpreters for the cosmos, offering a glimpse into realities beyond human perception and expanding the very definition of what it means to explore. Think of the internet not as a cold, mechanical grid of wires and servers, but as a living, breathing digital ecosystem. Data packets flow like nutrients through a forest, coursing along pathways that are constantly being optimized, rerouted around congestion, and seeking the most efficient path to their destination. This dynamic, self-organizing behavior didn't come from a single master plan. It emerged from the collective interaction of countless nodes, mirroring the way neurons fire in a brain or how mycelial networks exchange information between trees in a woodland. This is the power of network theory, the mathematical study of connections, and it reveals that the same fundamental architectural principles that sustain life on Earth could be the very thing that allows it to flourish on other worlds. At its core, network theory provides a universal language for describing how things are connected, whether those things are animals in a food web, people in a social group, or computers in a communications array. Two concepts are particularly powerful for engineers designing off-world infrastructure. The first is the small world phenomenon, popularized by mathematician Stephen Strogatz. This is the idea that most nodes in a network are not neighbors, but can be reached from every other node by a surprisingly small number of steps. It's the mathematical reason you're likely only 6 handshakes away from anyone on the planet, and it's also why information can travel across the globe so quickly. The second is the idea of scale-free networks, where a few highly connected hubs hold the entire system together, much like a handful of major airline hubs connect countless smaller airports. These aren't just abstract ideas, they are the blueprints for resilience. In an ecosystem, if a disease wipes out a common species, the network can often survive because those crucial hub species, while rare, maintain the web's stability. A systems engineer designing for Mars would point out that this natural redundancy is exactly what we need to build into our planetary colonies from the very beginning. Applying this wisdom starts with something as fundamental as power. A traditional, centralized power grid on Earth is a classic scale-free network. A few large power plants act as critical hubs. If one goes offline, blackouts can cascade across entire regions. For a Mars base, such a vulnerability would be catastrophic. Instead, engineers are designing decentralized microgrids inspired by the distributed robustness of a forest ecosystem. Imagine a habitat where every module has its own integrated solar panels and energy storage, creating a peer-to-peer network of power generation and sharing. If one module's system fails or is shaded by dust, the others can automatically reroute energy to it, just as nutrients are shunted through a fungal network to a tree in distress. This creates a resilient, web-like power system with no single point of failure, capable of adapting to failures and fluctuating energy demands without any need for central command. This same networked philosophy is revolutionizing how we think about communication in space. Current missions rely on a single, monumental hub, the Deep Space Network on Earth. While incredibly powerful, it creates a bottleneck and a vulnerability. The future of interplanetary communication looks less like a spoke and hub model and more like the Internet itself, a constellation of relays in orbit around Mars, the Moon, and other celestial bodies, all talking to each other and creating multiple redundant pathways for data. This small world design ensures that if one relay goes down, data packets can find another route, hopping from node to node until they reach their destination. It would mean astronauts on a Martian rover could have a continuous, high-bandwidth connection without worrying about dropping behind a hill and losing their line of sight to the main base, creating a communications web that is as resilient and adaptable as the natural networks that inspired it. Perhaps the most profound application of network theory is to the human element itself. A crew on a multi-year mission to deep space is itself a social network, and its psychological health is as critical as any life support system. Researchers studying isolated teams in analog environments, like the Concordia station in Antarctica, have found that the most successful groups aren't those with a strict, rigid hierarchy, a classic centralized network. Instead, they function more like a small world network where information, support, and leadership responsibilities are distributed. In these resilient teams, every member is connected to others through multiple strong and weak ties, preventing the isolation that can occur in a chain of command structure. This understanding is directly influencing the design of crew composition and mission protocols for future Mars missions, emphasizing the need for shared decision-making, cross-training, and creating a social infrastructure where interdependence is a built-in feature, not an emergency fallback. This entire approach forces us to reflect on a deeper truth about our place in the universe. We are not separate from the networks we study and emulate. We are nodes within them. Our survival on another planet will depend on our ability to consciously build and integrate into technological and social systems that mirror the interdependent webs of life that have sustained our species for millennia. It's a recognition that resilience doesn't come from independence and brute force, but from interdependence and graceful collaboration, a lesson written into the very structure of nature, waiting for us to decode and carry with us to the stars. Imagine a digital Petri dish, not filled with bacteria, but with thousands of computer-generated designs for a spacecraft antenna. These virtual prototypes are the primitive, single-celled organisms of this electronic ecosystem. Most are terrible, clumsy shapes that would fail instantly, but a few, by pure random chance, are slightly better than the others. They might have a bend that catches a signal a tiny bit more efficiently. This is the starting gun, an evolutionary algorithm, a process that ruthlessly mimics Darwin's theory of natural selection, now takes over. The best performing antennas are digitally selected to survive and reproduce. Their genetic code, the parameters that define their shape, are combined and randomly mutated, creating a new generation of offspring antennas. Some of these offspring inherit the good bend, others might have a new, weird fluke. The process repeats generation after generation, each time killing off the weak and propagating the strong. After thousands of these digital generations, something remarkable emerges from the electronic primordial soup, a bizarre, twisted, organic-looking antenna design no human engineer would ever have conceived of, yet it outperforms any traditional model by a significant margin. This is the uncanny power of evolutionary computation, a tool that is turning the immense, patient power of natural selection into a hyper-fast engine for cosmic innovation. The mathematical engine behind this process is known as a genetic algorithm, a concept pioneered by computer scientist John Holland in the 1970s. The core idea is breathtakingly simple yet profound. You don't need to be an expert in antenna design to create a perfect one. You just need to define the problem clearly and let evolution find the solution. As one aerospace researcher at NASA Ames Research Center put it, "We are not the designers anymore, we are the curators of a digital ecosystem. Our job is to set the rules of survival and then get out of the way." The process begins by defining a fitness function, a single, rigorous mathematical question that embodies the design goal. For an antenna, it might be maximize signal gain while minimizing mass. For a rocket engine turbine blade, it could be withstand maximum pressure with minimum material. This fitness function becomes the harsh, unyielding environment of the digital world. Designs that score well on this function get to pass their genes, their design parameters, to the next generation, while poor performers are mercilessly discarded. The true magic and the key to its success lies in the role of randomness introduced through the digital equivalents of crossover and mutation. Crossover involves taking two successful parent designs and splicing their parameters together, hoping their child might combine the best traits of both. Mutation, however, is the real wild card. It randomly tweaks a parameter, introducing a strange new feature, an unexpected bulge, an odd angle, a hole where there shouldn't be one. 99.9% of the time, this mutation is harmful and the design is cold. But that 0.1% of the time, it creates a revolutionary leap in performance, a design feature so counterintuitive and brilliant that it would never have occurred to a human mind constrained by convention and training. This is how evolution works in nature, and it's how these algorithms make their greatest discoveries. This approach shines brightest when tackling problems with multiple competing objectives, a scenario that defines almost every aspect of spacecraft design. A propulsion system needs to be incredibly powerful but also feather light. A habitat module must be strong enough to contain pressure but use as little material as possible to save on launch costs. This challenge is known as multi-objective optimization, and it's where human designers often have to make painful, subjective trade-offs. Evolutionary algorithms, however, thrive in this complexity. They don't seek a single best answer, but instead explore what's called the Pareto front, the entire set of optimal solutions where you cannot improve one objective without making another worse. The algorithm might present engineers with 100 different valid designs, one that is the absolute lightest, one that is the absolute strongest, and 98 others that represent every possible balance in between. This gives human experts a powerful menu of options, allowing them to make an informed choice based on the precise priorities of a specific mission. The practical results of this digital evolution are already flying in space and transforming aerospace manufacturing. Airbus has famously used generative design, a close cousin of evolutionary algorithms, to reimagine interior partition walls for its aircraft. The software produced a bizarre, bone-like structure that looked more like a dinosaur skeleton than an aircraft component. Yet, this organically formed design was 45% lighter than the traditional part while meeting all the same strength requirements. On a smaller scale, NASA used an evolutionary algorithm to design a communication antenna for a mission called Space Technology 5. The resulting antenna looked like a twisted, crumpled paperclip, but it provided exceptional performance across a wide range of frequencies, and it was compact and robust enough for the rigors of launch and deployment. These are not one-off experiments. They are becoming standard practice in labs from JPL to private companies like SpaceX, where shaving every gram of weight translates directly into millions of dollars saved and mission capabilities expanded. This entire paradigm forces us to confront a deep and almost philosophical question about the nature of innovation itself. For centuries, human progress has been driven by deliberate, conscious design, the brilliant insight of a lone inventor or a dedicated team. Evolutionary algorithms introduce a powerful, almost alien form of creativity, one that is emergent, bottom-up, and fundamentally reliant on randomness and failure. So, what is the true role of the human engineer in this new world? Are we becoming mere gardeners, planting the seeds of a problem, and then simply harvesting the best solution that grows, even if we don't fully understand why it works? The answer is more nuanced. The human role shifts from being the sole source of ideas to being the master of context. We define the problems, we set the constraints, we judge the outcomes, and most importantly, we provide the creative insight to interpret the often shocking results that the algorithm produces. It is a partnership between human intuition and machine-powered iteration, a collaboration that leverages the raw, exploratory power of evolution to break free from our own cognitive biases and discover solutions that lie in the vast, uncharted space beyond the limits of our imagination. Now, let's journey to one of the most Mars-like places on Earth, the McMurdo Dry Valleys of Antarctica. Here, in a landscape of frozen soil and bitter winds that scream down from the polar plateau, liquid water is virtually non-existent. The air is so dry and cold that it feels more like the surface of another planet than a part of our own. Yet, even in this profound desolation, life persists. Tucked away in the microscopic pores of rocks or frozen solid in the ice, resilient organisms like the legendary tardigrade or water bear wait. These tiny, 8-legged creatures can enter a state of suspended animation called cryptobiosis, desiccating their bodies and replacing their water with a special sugar that acts like biological glass, allowing them to withstand temperatures near absolute zero and the vacuum of space itself. They are living proof that the line between life and death can become blurry in the deep cold, a concept that is utterly revolutionizing how we think about designing technology for the icy moons of the outer solar system. The secret to survival in this frozen realm isn't about generating immense heat. It's about mastering the chemistry of water itself. This is where nature's biochemical ingenuity takes center stage. In the dark, frigid waters beneath the Arctic ice swim fish like the Antarctic toothfish. Their blood should freeze solid at these temperatures, their cells turning to deadly ice shards that would shred them from within. But they are protected by a miraculous class of molecules known as antifreeze proteins. As Dr. Arthur de Vries, a pioneering researcher who first discovered them, described, these proteins are like microscopic guards. They don't lower the freezing point of water in the way that car antifreeze does. Instead, they perform a delicate molecular dance. They bind to the surface of nascent ice crystals as they start to form, acting like a shield that prevents the crystals from growing larger. It's a form of targeted, non-toxic cryo-defense that keeps the fish's blood flowing as a liquid, even in an environment that should turn it to slush. This elegant biological solution is now inspiring a new generation of materials science for space exploration. Engineers are looking to create synthetic versions of these antifreeze proteins, or to develop surfaces that mimic their ice-inhibiting properties. The application is critical for any machinery operating on worlds like Jupiter's moon Europa or Saturn's moon Enceladus, both believed to harbor vast subsurface oceans beneath shells of ice. A submarine probe sent to explore these alien seas would face a constant threat of its own systems freezing shut. Intake valves, sensor ports, and manipulator arms could easily become clogged with ice. By coating these critical components with bio-inspired, ice-phobic materials, we could create machines that actively resist freezing, maintaining their functionality in environments that would paralyze conventional technology. This isn't just about convenience, it's about ensuring the success of billion-dollar missions to some of the most promising places in our solar system to find evidence of extraterrestrial life. The principle of cryopreservation, perfected by organisms like the tardigrade, extends beyond mere survival to the realm of storage and sustainability. For long-duration missions, especially those carrying biological samples or even human colonists in the far future, the ability to reliably preserve biological material is paramount. Current cryogenic freezers on the International Space Station are power-hungry pieces of equipment, but what if we could induce a state of synthetic cryptobiosis? Researchers are actively studying how to safely introduce protective sugars and other molecules into cells to put them into a stable, dormant state without the cellular damage typically caused by ice crystal formation. This technology could allow us to store seeds, medical supplies, or even cultured tissues for years on a Martian outpost with minimal energy expenditure, effectively creating a biological bank that remains viable almost indefinitely, ready to be revived when needed. It transforms a habitat storage closet from a passive cabinet into an active, biologically informed preservation system. Of course, sometimes the best strategy isn't to fight the cold, but to insulate against it with breathtaking efficiency. Here, the polar bear provides a masterclass in passive thermal management. Its famous fur is more than just a thick coat, it's a complex, multi-layered system. The outer guard hairs are actually transparent and hollow, trapping air and channeling ultraviolet light down to the bear's black skin, which efficiently absorbs the warmth. Beneath that lies a dense layer of underfur and a nearly 10-centimeter thick blanket of blubber. This entire system is so effective that a polar bear is virtually invisible to thermal imaging cameras. It loses so little heat that it barely registers against the frozen background. This natural stealth technology is a goldmine for engineers designing habitats and suits for extreme environments. NASA material scientists are taking this inspiration and running with it, developing advanced aerogels and metamaterials that mimic the structure of polar bear fur. These materials are designed to be incredibly lightweight yet possess an almost supernatural ability to trap air and prevent heat transfer. Imagine a next-generation spacesuit for exploring the permanently shadowed craters of the Moon's South Pole, where temperatures plunge to -250 degrees Celsius. The outer layer wouldn't be a simple fabric. It would be a bio-inspired composite with hollow fibers and a layered structure that creates a personal microclimate for the astronaut, drastically reducing the energy needed for active heating and allowing for longer, safer excursions into the ultimate deep freeze. This approach leverages the passive wisdom of evolution to create technology that is both more robust and more efficient. All of this research into Earth's extremophiles is coordinated and accelerated by programs at NASA and other space agencies, which maintain libraries of these organisms and fund research into their capabilities. The message from astrobiologists is clear. By studying the absolute boundaries of life on Earth, we are effectively drawing the blueprint for the future of biotechnology everywhere. The tardigrade, the Arctic fish, and the polar bear are more than just curiosities. They are consultants from a billion-year-old research and development department, showing us that the solutions to surviving the cosmic cold are not always found in generating more power, but in working smarter with the chemistry and physics of the environment itself. They challenge our very definitions of what is possible, blurring the line between a living organism and a sophisticated piece of engineering, and forcing us to wonder if the most advanced technology for the future of space exploration is already here, waiting patiently in the ice. Deep within the ruins of the Chernobyl nuclear power plant, in the eerie stillness of the exclusion zone, a silent and astonishing revolution is taking place. Growing up the walls of the reactor's remains, a black fungus is thriving. It isn't just surviving the intense, lingering radiation, it's seemingly feeding on it. Scientists discovered that these fungi, like Cladosporium sphaerospumum, are rich with melanin, the same pigment that gives human skin its color and protects it from the sun's ultraviolet rays. But in these organisms, the melanin acts differently. It appears to absorb the high-energy radiation and convert it into a form of chemical energy the fungus can use for growth, a process dubbed radiosynthesis. This isn't an isolated miracle of nature. In deserts and nuclear waste sites around the world, a bacterium named Deinococcus radiodurans holds the title of the world's toughest organism. It can withstand radiation doses thousands of times greater than what would be lethal to a human, not by blocking the radiation, but by possessing an almost supernatural ability to repair its shattered DNA with breathtaking speed and accuracy. These extremophiles don't see radiation as a threat. They see it as just another part of their environment to be managed and even exploited, offering us a radical new playbook for surviving the most hazardous environments in the cosmos. The conventional human approach to radiation shielding has always been one of brute force mass. We pile on layers of lead, polyethylene, or water, anything dense enough to absorb and block the relentless hail of high-energy particles that fill space. This strategy works, but it comes at a catastrophic cost: weight. every kilogram of passive shielding launched from Earth requires a small fortune in fuel, severely limiting the size of our spacecraft and the duration of our missions. The organisms at Chernobyl and in our labs suggest a completely different path, one of active biological defense. As one medical researcher working with NASA analog studies explained, we're learning that the best shield might not be a wall but a system. It's not about stopping every particle, it's about managing the damage they cause and repairing it faster than it can accumulate. This biomimetic approach moves us from a paradigm of passive blocking to one of active resilience, a shift that could make long-duration spaceflight and off-world colonization truly viable. This new philosophy is already taking physical form in laboratories through the development of advanced, bio-inspired materials. One of the most promising avenues involves engineering radiation, absorbent materials that mimic the protective compounds found in these hardy organisms. Melanin, particularly the specific type found in the Chernobyl fungi, is a major focus. Researchers are not just extracting this melanin, they are creating synthetic versions of it and experimenting with infusing it into everything from the plastics of spacecraft hulls to the fabrics of spacesuits. Imagine a future where an astronaut's suit is lined with a thin, flexible layer of melanin-based polymer. As galactic cosmic rays pass through it, the material would actively absorb and dissipate their energy, significantly reducing the dose that reaches the wearer's body. This wouldn't require carrying immense weight. It would integrate protection directly into the material structure of everything we send into space, turning the entire vehicle into a smart shield. The lesson from Deinococcus radiodurans, however, isn't about absorption, it's about repair. This bacterium's incredible resilience comes from having multiple copies of its genome and a highly efficient toolkit of DNA repair enzymes that can swiftly reassemble its genetic code after it has been blown apart by radiation. This has profound implications that extend beyond biology to the realm of electronics. Spacecraft avionics are notoriously vulnerable to single-event upsets, where a single high-energy particle can flip a bit in a computer's memory, causing errors, glitches, or even total system failure. Inspired by the bacterium's redundant and self-repairing genome, engineers are designing fault-tolerant computing systems. These systems don't just have backup chips, they have architectures that constantly check for and correct errors in their own data, automatically rewriting corrupted code and rerouting processes around damaged components. It's a form of digital DNA repair, creating electronics that can heal themselves from the inside out, ensuring mission-critical systems remain operational even when bombarded by the worst the sun can throw at them. Perhaps the most elegant and sustainable application of this biomimetic thinking involves turning the alien environment itself into our shield. This is the principle of in situ resource utilization, or ISRU, taken to a new level. Why launch all our shielding from Earth when we can use what's already there? On the Moon or Mars, this means using regolith, the loose soil and rock that blankets the surface. Architects and engineers are designing habitats that are either buried beneath this regolith or constructed from 3D printed blocks of it, using the planet's own mass as a barrier against radiation. But we can go even further, learning from the fungi that thrive in the most unlikely places. Experiments on the International Space Station, like the Expose R2 project, have placed samples of these melanin-rich fungi outside the station to directly expose them to the full fury of space radiation. The goal is to see just how effective they are at protecting themselves, and by extension, how we might one day cultivate them. Imagine a future where we don't just pile dirt on our habitats, but we line their inner walls with a living, growing layer of radiation-absorbing fungal biomat. This living shield would not only protect the inhabitants but could potentially even contribute to the habitat's air purification or food production systems, creating a truly integrated, biological life support system that actively works with us to manage the dangers of our new environment. This entire endeavor forces us to confront a critical strategic question about the future of our presence in space. Do we continue our current path, which is ultimately unsustainable, relying on launching every gram of protection from Earth in an expensive and limiting cycle of dependence? Or do we embrace a new model of sustainable self-reliance, where we learn to use local materials and biological principles to create systems that are not just placed on another world, but are truly of that world? The first option offers a known but incredibly costly and fragile solution. The second option, inspired by the humblest of Earth's organisms, is far more ambitious. It requires a deeper understanding of both physics and biology, and a willingness to partner with nature rather than simply overcome it. But it promises a future where our outposts on Mars and beyond are not sterile, pressurized bubbles living on borrowed time, but resilient, growing, and ultimately sustainable extensions of life itself, capable of weathering the storms of deep space for generations to come. Picture a robotic drone not soaring through thin Martian air, but descending through the hazy, orange gloom of Titan's atmosphere. Below it lies not water, but a vast, frigid sea of liquid methane, with waves slowly rolling under the pull of Saturn's gravity. This isn't science fiction. It's the mission profile for NASA Dragonfly, a rotorcraft designed to explore this alien moon. But flying on Titan is an entirely different challenge from flying on Earth. The atmosphere is 4 times denser, the gravity is weaker, and the fluid it moves through is cryogenic methane, not nitrogen and oxygen. To navigate this strange environment, engineers aren't just building a bigger drone. They are turning to the ultimate experts in moving through thick, dynamic fluids, the creatures of our own oceans and skies. The fundamental challenge boils down to a principle every swimmer or cyclist intuitively understands: drag. Drag is the resistance a fluid, whether a liquid or a gas, exerts on an object moving through it. Overcoming drag consumes enormous energy, and in the constrained world of a space mission, energy is the ultimate currency. This is where biomimicry becomes a power-saving necessity. For over 400 million years, aquatic and aerial animals have been refining their shapes to slip through their respective fluids with minimal effort. A tuna's sleek, torpedo-like body isn't just for speed. It's a masterclass in reducing pressure drag, the force that builds up in front of a moving object. Its smooth skin and specialized scales minimize viscous drag, the friction caused by the fluid sliding along its surface. As one aerodynamics expert from the Johns Hopkins Applied Physics Laboratory, the lead institution for Dragonfly, noted, "We aren't just copying a shape, we're reverse engineering an evolutionary strategy for efficiency." The goal is to design a vehicle that feels like it belongs in the fluid it's moving through, rather than fighting against it. This pursuit of efficiency has led to some of the most fascinating breakthroughs in biomimetic wing design. Dragonfly's rotors, for instance, can't be simple scaled-up versions of drone propellers. On Titan, with its thick atmosphere and low gravity, they need to generate immense lift without spinning so fast they waste precious power or create turbulent, unstable vortices. The inspiration for this comes from the world of insects and hummingbirds, masters of hovering flight in Earth's dense air. Their wings aren't flat plates, they are complex, cambered structures that twist and flex with each stroke. This dynamic morphing allows them to generate lift on both the upstroke and downstroke, a trick no rigid rotor can perform. Dragonfly's engineers have studied this intently, designing rotors that are optimized for the specific fluid density of Titan. Their shape and pitch carefully calculated to achieve maximum lift with a slow, efficient, and stable rotation that conserves energy for its nuclear battery throughout a mission planned to last for years. But the influence of fluid dynamics extends far beyond the shape of wings. It delves into the very way energy is managed in moving systems. A critical concept here is vortex shedding. When a fluid flows past a blunt object, like a bridge pillar or a submarine periscope, it can't follow the surface perfectly. It separates and curls off into swirling vortices on the downstream side. This alternating shedding creates oscillating forces that can make the object vibrate, a phenomenon that led to the infamous collapse of the Tacoma Narrows Bridge in 1940. In machinery, this vibration wastes energy, creates noise, and can lead to catastrophic metal fatigue. Nature, however, has found elegant solutions. The bumps on a humpback whale's flipper are a famous example. These tubercles break up the flow of water over the flipper, preventing the formation of large, energy-wasting vortices and actually enhancing lift. This principle is now being applied to the design of turbomachinery, the compressors, fans, and pumps that are the hearts of environmental control and life support systems on spacecraft. By giving the blades inside these machines a biomimetic, tubercle-like leading edge, engineers can make them more efficient, quieter, and far more resistant to the destructive vibrations caused by vortex shedding, a critical upgrade for systems that must run reliably for decades on a distant world. The ultimate lesson Titan teaches us is that fluid dynamics is not a universal constant. It is a conversation between an object and its specific environment. The rules of movement change dramatically with a fluid's density and composition. A vehicle designed for the wispy thin air of Mars would be hopelessly inefficient and unstable in Titan's soupy atmosphere. This means engineers can't have a one-size-fits-all solution. They must become fluent in the language of different fluids, designing vehicles that are exquisitely tailored to their destination. Dragonfly is a perfect embodiment of this philosophy. It is not a general-purpose explorer. It is a specialist, a creature designed for one specific alien environment. Its every curve and rotor angle a testament to the principle that to conquer a new world, we must first learn to move through it with the effortless grace of a native. High on a windswept alpine rockface where nutrients are scarce and the sun beats down relentlessly, a patch of lichen clings to life. This isn't a single organism, but a partnership, a perfect fusion of fungus and algae. The fungus provides the structure, a protective anchor that gathers minute traces of minerals from the rock. The algae, sheltered within, uses that anchor and the sunlight to photosynthesize, creating food that feeds both partners. Alone, neither could survive in this harsh place. Together, they not only survive, they thrive. This ancient pact, known as mutualism, is one of nature's most powerful strategies for conquering challenging environments, and it offers a radical new blueprint for how we might live and work in space, moving beyond the concept of standalone machines and toward truly integrated, symbiotic systems. This philosophy of symbiotic engineering represents a fundamental shift from how we've traditionally approached technology. For most of the space age, our approach has been modular and isolated. A life support system here, a power unit there, a habitation module somewhere else, all connected by wires and pipes, but essentially operating as independent pieces. The problem with this model is its inherent fragility, much like a lone algae cell on a dry rock. If one module fails, it can cripple the entire operation. Symbiotic engineering, inspired by ecologists who study these intricate partnerships, proposes we design systems that are more like lichen. deeply intertwined, where the success of one component is intrinsically linked to and supportive of the others. A systems designer working on advanced habitat concepts might describe it as creating a technological ecosystem where waste is an obsolete concept, and every output is a valuable input for another part of the system. The most critical application of this is in the creation of sophisticated closed-loop systems. The International Space Station has a partially closed-loop system for water recycling, but we can go much further, inspired by the flawless cycles of a mature ecosystem. Imagine a Mars habitat where the carbon dioxide exhaled by the crew isn't just scrubbed from the air and stored as waste. It becomes the primary nutrient for an adjacent aeroponics bay. In this bay, genetically modified plants or algae, optimized for spaceflight, would greedily absorb the CO2. Under specialized LED lights tuned to their photosynthetic needs, they would not only produce fresh oxygen for the crew, but also be harvested for food. The inedible plant matter, along with other organic waste, wouldn't be jettisoned. It would be fed into an anaerobic digester, a synthetic stomach, where bacteria would break it down to produce nutrient-rich fertilizer for the plants and potentially methane gas that could be used as a backup fuel source. In this tightly coupled cycle, the line between human life support and food production blurs into a single, self-reinforcing loop, dramatically reducing the need for resupply from Earth and moving toward true self-sufficiency. This principle of mutual benefit extends powerfully to the relationship between humans and machines, moving far beyond simple command and control. Consider the dynamic of a wolf pack on the hunt. There is a clear objective, but the roles are fluid. The pack moves as a cohesive unit, with individuals communicating constantly, adapting their positions in real time, and leveraging each other's strengths to achieve a goal that would be impossible alone. This is the model for the next generation of human-robot collaboration in space. Instead of an astronaut manually remote controlling a single rover with a joystick, imagine a future astronaut on a Martian EVA serving as the hub of a robotic pack. A smaller, agile scout robot might range ahead, using its sensors to map the terrain and identify hazards, relaying that data directly into the astronaut's helmet display. A larger, strength-enhanced utility robot would work alongside the human, acting as a pack mule carrying tools and samples, or physically stabilizing a heavy object while the astronaut performs delicate work with their human dexterity. The robots handle the repetition, the heavy lifting, and the hazardous reconnaissance. The human provides the overarching strategy, contextual understanding, and fine motor skills. This isn't a master-slave relationship. It's a symbiotic partnership where both human and machine capabilities are amplified by the presence of the other. We can find a profound, if cautionary, example of attempting to create a closed-loop symbiotic system here on Earth with the Biosphere 2 project. In the early 1990s, 8 people sealed themselves inside a 3-acre glass-enclosed environment in the Arizona desert, intended to be a fully self-sustaining miniature Earth. While the project ultimately struggled with balancing its atmospheric gases and food production, it provided invaluable lessons. The failure of one system, like the unexpected proliferation of soil microbes that consumed oxygen, had cascading effects throughout the entire closed environment. This highlights the incredible complexity and delicate balance of symbiotic systems. It teaches us that for a future Mars habitat, redundancy and system resilience are not optional. They are the very pillars of survival. You cannot have just one method of oxygen production. You need 2 or 3, perhaps a primary system using algae, a backup using electrolysis, and the ability to grow emergency fast-sprouting plants. The lesson from Biosphere 2 isn't that closed-loop systems are impossible. It's that they require a deep understanding of interconnections and a design philosophy that expects and can adapt to unexpected feedback loops, much like a natural ecosystem evolves over time. This inevitable shift toward deep interdependence between humans and their supporting technology forces us to confront some of the most complex ethical questions we will face as a spacefaring species. As we become more reliant on these symbiotic systems for our air, our water, our food, and even our physical safety, where does healthy interdependence end and vulnerable dependency begin? If the AI governing the habitat's atmospheric controls develops a flaw, how much autonomy should it have to make critical decisions without human oversight? And in a crisis, if a life-saving resource is limited, how does the system decide between prioritizing the human crew or maintaining the robotic and biological systems that keep them alive in the long term? These are not abstract dilemmas. They are fundamental design parameters that will define the relationship between future astronauts and their mechanical and biological partners. The goal of symbiotic engineering is not to create a world where humans are passive passengers in a machine-run zoo, but to forge a new kind of active, balanced partnership, a technological lichen where human ingenuity, biological resilience, and artificial intelligence combine to create something far stronger and more adaptable than any one of them could ever be alone. Our bodies are not designed for the silent, sunless expanse of space. They are finely tuned instruments calibrated to the rhythmic pulse of a planet. For every living thing on Earth, from the mightiest whale to the simplest bacterium, existence is governed by an intricate symphony of internal clocks. These circadian rhythms, orchestrated by a tiny region in the brain called the suprachiasmatic nucleus, sync our sleep, our hormones, our alertness, and even our cellular repair to the reliable 24-hour cycle of light and dark. This is the deep biological metronome that has ticked for billions of years, but aboard a spacecraft orbiting Earth every 90 minutes, experiencing 16 sunrises and sunsets in a single day, that metronome is thrown into chaos. The result is more than just jet lag. It's a fundamental disorientation that can fray nerves, cloud judgment, and erode the mental resilience of a crew cut off from the planetary rhythms that shaped our very evolution. This scientific understanding of biological timekeeping is the foundation of chronobiology, a field that is now critically informing the engineering of habitats for long-duration missions. As Dr. Erin Flynn Evans, head of the NASA Ames Research Center's Fatigue Countermeasures Laboratory, has observed, "We can't change human biology, but we can design environments that respect it." In space, we have to become architects of time itself. The most immediate and powerful application of this is in the design of lighting systems. The harsh, static fluorescent lighting of early space stations has been replaced by a new generation of adjustable LED systems, like the one installed on the International Space Station. These aren't just simple on-off switches, they are sophisticated tools for physiological regulation. In the morning, they can emit a strong, blue-enriched light that suppresses melatonin and promotes alertness, effectively creating a synthetic sunrise inside the metal hull of a spacecraft. As the day progresses, the lights gradually shift to a warmer, softer, amber hue, gently cueing the body to wind down and prepare for sleep, mimicking the fading light of a terrestrial evening. This daily orchestration of light is a form of non-pharmaceutical intervention, a way to anchor the crew's circadian rhythms to an artificial but stable day-night cycle, combating insomnia and fatigue while bolstering overall well-being. However, the challenge of time extends far beyond the 24-hour cycle. On a mission to Mars, which lasts over 2 Earth years, crews will also have to contend with entirely new seasonal patterns. A Martian year is 687 Earth days long, with seasons that last roughly twice as long as our own. The planet's axial tilt is similar to Earth's, meaning it will experience seasonal changes in sunlight, which could impact the operation of solar panels and the psychological experience of the crew. Architectural design must therefore accommodate these long-term cycles. Imagine a habitat on Mars designed with a central, transparent atrium. During the long summer months, this space could function as a vibrant greenhouse, flooded with sunlight to support plant growth and provide a connection to a living, growing environment. But as the Martian winter approaches and dust storms may obscure the sun for weeks, the architecture would need to adapt. Retractable shielding could close over the atrium, transforming it into a well-insulated communal space lit by the same circadian lighting systems, protecting both the crew and the machinery from the harsh seasonal shift. The habitat itself would need to breathe and change with the Martian year, its design reflecting an understanding of long-term temporal patterns, not just daily ones. The final and perhaps most complex layer of this temporal design involves the social and operational schedules of the crew themselves. Here, chronobiology merges with data science. By studying the natural peaks and troughs in human cognitive performance throughout the day, the post-lunch dip in alertness, the evening surge in creativity for some mission planners can use sophisticated scheduling algorithms to optimize the crew's workload. These algorithms could automatically assign critical, high-focus tasks like complex repairs or delicate experiments to periods when the crew's circadian rhythms predict peak alertness based on their individual sleep-wake cycles. Conversely, routine maintenance or physical exercise could be scheduled for natural energy lulls. This isn't about micromanaging every minute. It's about creating an intelligent rhythm of work and rest that aligns with human biology to maximize both safety and productivity. It turns the schedule from a simple spreadsheet into a dynamic, responsive tool that helps the crew work with their bodies, not against them. The lessons learned from decades of living on the International Space Station provide a powerful testament to the importance of these rhythms. Astronauts consistently report that maintaining a strict sleep schedule and having a clear delineation between work and personal time is one of the most effective strategies for preserving mental health. The simple act of observing a weekend, of having a shared meal at the same time each day, or of celebrating holidays creates temporal landmarks that break the monotony of a long-duration mission. These rituals provide a sense of progression and normalcy, a way to mark the passage of time that feels human and meaningful. As we venture further from Earth, where a video call home will have a delay of 20 minutes or more, these self-generated rhythms will become even more critical. They will be the internal clockwork that keeps a crew not just physically healthy, but psychologically connected, synchronized not by the sun of a world they left behind, but by the shared, deliberate tempo of a life they are building together in the vast and timeless silence between the stars. Watch a honeybee, its legs heavy with pollen, return to the hive and begin the meticulous work of adding another cell to the comb. What emerges is a masterpiece of geometric precision, a wall of perfect hexagons, each one fitting flush against its neighbors without a single gap or wasted space. This isn't just an aesthetic choice, it's the result of millions of years of evolutionary pressure toward maximum efficiency. The bee doesn't know advanced mathematics, but through instinct, it has solved one of geometry's most enduring puzzles: how to partition a surface into equal areas using the least possible perimeter. For the bee, this means using the minimum amount of precious wax to create the maximum amount of secure storage for honey and larvae. For an engineer designing a spacecraft, where every cubic centimeter and every gram are fought over with intense fervor, this natural principle of optimal packing becomes one of the most valuable tools in the entire cosmic design toolkit. The mathematical field that studies these problems is known as packing theory, and it provides the formal rules behind nature's intuitive genius. It asks questions like, what is the most efficient way to arrange objects in a given space? Two concepts are particularly powerful. The first is tessellation, the covering of a surface with one or more geometric shapes with no overlaps and no gaps. The honeycomb is the classic example of a regular tessellation using hexagons, but nature is full of other irregular tessellations, like the scales on a snake or the cracks in drying mud. The second is sphere packing, which deals with the arrangement of spheres in a container. While it might seem abstract, this principle dictates everything from the structure of a metal alloy to the way fruits like oranges are stacked in a crate. As mathematician and designer Thomas Hull points out, these aren't just abstract puzzles, they are the fundamental rules of how matter organizes itself efficiently under constraint. When you are building for space, constraint is the entire game. This geometric wisdom is now being directly injected into the architecture of future space habitats. The dream of a large, spacious module on the Moon or Mars is constrained by the brutal physics of launch. Everything must fit inside the cramped, cylindrical payload fairing of a rocket. The solution is modularity, building a large habitat from many smaller, interconnected units. But how do you design those units so they pack efficiently for the journey, yet assemble into a spacious and usable living environment? This is where tessellation shines. Engineers are designing habitat modules with hexagonal or pentagonal cross-sections. During launch, these modules can be stacked and nested together like a puzzle, perfectly utilizing every available inch of the rocket's diameter. Once deployed on the lunar surface, these same modules can be interconnected along their flat facets, creating a robust hive-like structure that is naturally strong against pressure differentials and maximizes the usable volume for the crew, turning the launch constraint into an architectural feature. The challenge of packing extends beyond the large-scale habitat to the mind-boggling complexity of organizing the thousands of items needed for a mission. A spacecraft storage bays are a three-dimensional jigsaw puzzle of unparalleled importance. Here, the principle of sphere packing finds a surprising application. While you're not storing spheres, the concept informs the design of standardized containers. By using containers of a few optimized sizes and shapes, ones that can be tightly nested together, engineers can maximize the packing density of cargo holds. This is why so much equipment on the International Space Station is housed in identically sized racks and lockers. It creates a modular packing system where every item has a known volume, and the entire storage system can be treated as a complex geometric packing problem, ensuring no space is wasted and every tool is accessible without a costly and time-consuming unpacking of everything else. Perhaps the most revolutionary merger of geometry and manufacturing is happening in the realm of 3D printing, specifically with a pattern known as the Voronoi tessellation. Named after the mathematician Georgy Voronoi, this pattern describes how space can be partitioned into regions based on distance to a set of seed points. The result is that familiar, organic-looking structure you see inside a bird bone or a piece of coral, a web of seemingly random polygons that create a lattice. This pattern is nature's way of creating immense strength with minimal material. Engineers are now using algorithms to generate Voronoi patterns to design the internal structure of 3D printed components. For a bracket or a structural beam destined for a space station, this means you can print it as a solid object on the outside for mounting, but with a complex, lightweight Voronoi lattice on the inside. This approach cuts the component's weight by 60 or 70% while maintaining over 90% of its strength, a staggering efficiency gain that directly translates to lower launch costs or the ability to carry more scientific instruments. NASA is actively pursuing these strategies in projects aimed at sustainable lunar exploration. The space agency has investigated using 3D printing with regolith to construct habitats, and the internal designs for these structures frequently employ Voronoi or other bio-inspired lattices to ensure they are light and strong enough to withstand the challenges of the lunar environment. This isn't just about building a shelter, it's about growing an infrastructure, using the mathematical rules of efficient form to create a presence on another world that is both resilient and resource-light. This relentless pursuit of efficiency, however, leads us to a deeply human question that transcends engineering. Where is the line between optimal efficiency and human comfort? A beehive is a marvel of packing, but it is not designed for the psychological well-being of its inhabitants. A spacecraft or habitat designed with absolute geometric efficiency could feel cramped, claustrophobic, and maze-like. Will astronauts thrive in a perfectly packed hexagonal module, or will they need the psychological relief of irregular spaces, higher ceilings, or windows that break the geometric pattern? The ultimate design challenge is not just to pack things efficiently, but to pack them in a way that leaves room for the human spirit, to create environments that are not just machines for living, but homes that support morale, creativity, and well-being on a mission that stretches for years. The answer will likely be a hybrid, a blend of the bee's ruthless efficiency in the storage and mechanical bays, and a more spacious, psychologically considered design in the living quarters, proving that the best cosmic designs are those that serve both the laws of physics and the needs of the human heart. Deep in the lightless world of the ocean's midnight zone, where vision is utterly useless, a humpback whale sings a complex and haunting song. This low-frequency melody can travel for thousands of miles through the watery depths, a slow, resonant communication that connects individuals across an immense, dark expanse. The whale doesn't fight the limitations of its environment. It leverages the unique properties of water itself to create a sonic network that blankets the ocean. Now imagine a similar scenario not on Earth, but on the hazy shores of Titan's methane lakes or in the subsurface ocean believed to churn beneath the icy crust of Europa. In these alien environments, where visibility might be near zero and traditional radio signals could be absorbed or distorted, the most reliable way to see, navigate, and communicate might not be with light or radio waves, but with sound. This is the promise of bioacoustics, the study of how life uses sound, and it's providing a revolutionary toolkit for engineering technology that can listen to and interpret the symphony of other worlds. The field of bioacoustic engineering is built on a simple but profound realization. Animals have been solving extreme communication and sensing challenges for millions of years. As Dr. Laura Rogers, a planetary scientist specializing in acoustics, explains, we tend to be a visually dominant species, so our first instinct is to send cameras everywhere. But so much of the universe is hidden from view in clouds, in liquids, in darkness. By learning from animals that have mastered these non-visual realms, we're essentially giving our robots new senses, allowing them to perceive environments that are completely invisible to us. This approach moves beyond simply building a better microphone. It involves decoding the biological algorithms and physical structures that allow a dolphin to mentally visualize a fish hiding in sediment or an owl to pinpoint a mouse under a foot of snow based solely on sound. One of the most immediate applications of this knowledge is in the design of sophisticated sonar systems for planetary exploration. Dolphins don't just emit a single ping and listen for an echo. They use a complex array of clicks and whistles, analyzing the returning signals to build a detailed three-dimensional sound picture of their surroundings. They can distinguish between a rock and a fish based on the subtle acoustic textures of the returning echo. Engineers are now developing biomimetic sonar for potential submersible probes destined for worlds like Europa. These systems would use arrays of transmitters and receivers to create a rich, 3D acoustic map of a pitch-black alien ocean, capable of identifying the topography of an icy ceiling, the shape of a hydrothermal vent, or even the unique density of a potentially interesting biological formation. This would allow a robotic explorer to see its surroundings through sound, turning a completely lightless environment into a mapped and navigable space. But sending out sound is only half the equation. A probe must also be able to listen clearly through the cacophony of an alien world. This is where another bio-inspired breakthrough comes into play: noise filtration algorithms. On Mars, for example, the Perseverance rover carries microphones, and the audio it has sent back is dominated by the relentless howl of wind, filtering out that noise to hear the subtle sounds of the Martian environment. The hum of the rover's own systems, the crunch of its wheels on regolith, or the whisper of a dust devil passing by is a monumental task. Here, engineers are turning to the auditory cortex of animals like the prairie dog. Despite living in large, noisy colonies, these animals can distinguish the specific alarm calls of their kin from the general background din. By studying the neural mechanisms behind this auditory filtering, computer scientists are developing new algorithms that can isolate and enhance specific sounds of interest while suppressing ambient noise, allowing future missions to listen with crystal clarity to the whispers of another world. The pursuit of clear listening also extends to the very design of the sensors and platforms themselves. For a mission like Dragonfly, the rotorcraft destined for Titan, the noise of its own rotors could easily drown out any scientific observations. The solution may lie in the silent flight of owls. Their wings possess a unique combination of a comb-like leading edge and a soft, fringed trailing edge that breaks up turbulent airflow, the primary source of noise in flight. By applying similar textures to the edges of Dragonfly's rotors, engineers could drastically reduce their acoustic signature, making the vehicle quieter and allowing its onboard microphones to listen for the sounds of methane rain falling on Titan's surface or the distant rumble of cryovolcanoes without interference from its own machinery. The data we are already gathering is providing a fascinating glimpse into how different other worlds will sound. The audio recordings from the Perseverance rover reveal that sound behaves differently in the thin Martian atmosphere. Higher frequency sounds travel a much shorter distance than lower ones, meaning a complex piece of music would arrive at your ear distorted, with its high notes attenuated. On a world like Venus with its incredibly dense supercritical atmosphere, sound would travel faster and farther, and its properties would be stranger still. This has profound implications for both science and human exploration. Seismometers are essentially specialized microphones that listen for the rumble of Mars quarks, and understanding the acoustic properties of the atmosphere is key to interpreting their data correctly. For future astronauts, communicating outside a habitat on Mars would be difficult. Without a radio, your voice would barely carry, and you would struggle to hear someone shouting just a few dozen feet away. This forces us to expand our very definition of exploration. We are not just sending robots to take pictures of other planets. We are sending them to listen, to become our ears in environments where our own senses are completely inadequate. The sounds of an alien world, the whisper of wind across a different kind of sand, the patter of methane rain, the groan of ice shifting over a hidden sea, will tell us a story that cameras alone cannot. They will provide a visceral, immersive understanding of these distant places, allowing us to experience them not as silent, sterile postcards, but as dynamic, living worlds with their own unique voices, waiting for us to learn how to listen. Imagine a human embryo developing in the womb, a microscopic sphere of identical cells embarking on the most complex construction project in the known universe. Without a single external blueprint, these cells begin to differentiate, to fold, and to migrate, organizing themselves into the intricate layers that will become a brain, a heart, a skeleton. This self-directed process of creating form, known as morphogenesis, is biology's ultimate manufacturing system. It doesn't require a factory. It uses local materials and energy to build structures of breathtaking complexity that are perfectly adapted to their environment. Now picture that same principle applied not in a womb, but in the silent, weightless void of orbit. Instead of cells, imagine a swarm of smart particles or a tank of special gel. Instead of growing a person, imagine growing a space station module or a massive telescope array, not by assembling it with robots, but by guiding it to assemble itself, to essentially come alive and grow into its final form. This is the radical frontier of in situ manufacturing, where we are learning to code matter itself to behave as if it were biological, turning the entire cosmos into our workshop. This shift in philosophy is forced upon us by the simple, brutal economics of gravity. Launching anything from Earth's deep gravity well is phenomenally expensive and limiting. We cannot possibly launch all the materials needed for a permanent moon base or a Mars colony in one go. The rockets would be the size of skyscrapers. The solution, then, is to become like the embryo, use what's already there. This is the promise of self-assembly and programmable matter. Self-assembly is the process by which disordered components autonomously organize into a structure or pattern, a phenomenon seen everywhere from crystals forming to proteins folding. Programmable matter takes this a step further. It refers to materials whose physical properties, their shape, stiffness, or even optical characteristics, can be digitally controlled and changed on demand. A developmental biologist would see a direct parallel to the morphogenetic fields that guide an embryo's growth, where chemical gradients and genetic signals tell cells where to go and what to become. Engineers are now trying to create a similar set of rules for non-living matter, designing smart particles that can be programmed to respond to a signal, be it a magnetic field, a specific wavelength of light, or a change in temperature, and spontaneously organize themselves into a pre-designed structure. One of the most tangible expressions of this is the emerging field of 4D printing. Traditional 3D printing creates a static object. 4D printing adds the dimension of time. It involves printing objects with smart materials, often multi-layered composites, that are programmed to transform their shape or function after the printing process is complete, usually in response to an environmental trigger like water, heat, or light. A simple analogy is a flat-packed IKEA table that, when you pour a glass of water on it, spontaneously folds and assembles itself into the finished product. For space applications, this is revolutionary. Imagine sending a compact, flat payload to the moon. Once unpacked and exposed to the intense, unfiltered sunlight, the material warms up and begins to fold, curl, and lock into place, transforming from a flat sheet into a parabolic communications dish or a sturdy shelter, all without a single astronaut needing to risk a spacewalk to bolt it together. This technology turns passive cargo into active, transforming systems that build themselves on arrival. The International Space Station has become a vital testbed for these bio-inspired manufacturing techniques, particularly in the realm of bioprinting. While the goal isn't to grow organs in space, yet scientists are using the unique microgravity environment to experiment with printing biological tissues. On Earth, gravity is the enemy of bioprinting. Dense cell-laden structures collapse under their own weight before they can form stable tissue. But in the weightlessness of orbit, researchers can print with incredible precision using extremely delicate bioinks, creating intricate, self-supporting vascular structures that would be impossible to manufacture on Earth. The company TechShot, now part of Redwire Space, successfully operated a bioprinter on the ISS that printed cardiac and vascular structures. This research is a double breakthrough. It paves the way for potentially creating medical supplies for astronauts on long-duration missions, and it provides a profound proof of concept for using biological growth processes to inform how we might one day print with regolith or metals in space, building structures layer by layer with the precision of a body building a bone. This vision of growing structures like bones gets to the very heart of the morphogenetic analogy. Our bones are not static pillars. They are dynamic, living tissues that continuously remodel themselves in response to stress, a principle known as Wolff's Law. The trabecular lattice inside a bone is a masterpiece of topological optimization, placing material exactly where it's needed for strength and removing it where it's not, resulting in a structure that is both incredibly strong and remarkably lightweight. Engineers are now applying this same principle to in situ manufacturing. The idea is to use a process akin to additive manufacturing, but with a smart algorithm that continuously analyzes the stresses on a growing structure, be it a habitat wall or a spacecraft component, and adjusts the deposition of material in real time, just as osteoblasts and osteoclasts do in response to mechanical load. This would result in structures that are perfectly adapted to the specific gravitational forces, thermal stresses, and vibrational loads of their alien environment, whether it's the 1/6 gravity of the Moon or the microgravity of an asteroid. The structure wouldn't just be built, it would be grown in the most engineering sense of the word, evolving its form to meet the demands of its purpose. All of this progress, however, inevitably pulls us toward a profound and unsettling ethical frontier. As we incorporate more biological principles and eventually biological materials themselves into our technology, where do we draw the line between a machine and an organism? If we create a habitat that can self-repair by using embedded bacterial spores that secrete a healing biomineral, is that habitat still just a building, or does it possess a rudimentary form of life? If we use guided fungal mycelium to grow structural components that are alive and metabolizing, what are our ethical responsibilities toward that structure? These are not questions for a distant future, they are design considerations for the next few decades. The field of biomimicry began with simply copying shapes from nature. We are now moving toward a deeper integration, copying processes, and ultimately incorporating biology itself into our technological systems. This forces us to confront the very nature of what we are building. Are we creating sterile, inert tools, or are we seeding a new kind of biotechnological hybrid ecosystem across the solar system? And what are the moral implications of creating such a thing? Consider the entire Library of Congress, every book, every photograph, every sound recording, a vast treasure of human knowledge spanning centuries. Now imagine compressing all of that information down into a format so dense it could fit inside a single sugar cube. This isn't a thought experiment from far future science fiction. It's a staggering reality of biology happening inside the nucleus of every one of your cells. DNA, the molecule of life, is quite possibly the most efficient, durable, and compact data storage system ever devised by nature. For long-duration space missions, where every gram of payload is precious and the integrity of data must be maintained for decades or even centuries in the harsh environment of space, this biological blueprint offers a revolutionary solution to one of our most pressing challenges: how to preserve the entirety of human knowledge and mission-critical data when traditional digital systems are vulnerable to failure. This potential is rooted in the fundamental principles of information theory, a field pioneered by Claude Shannon, which deals with the quantification, storage, and communication of information. At its core, information is information, whether it's encoded in the zeros and ones of a computer or the four chemical base pairs adenine, guanine, cytosine, and thymine that form the rungs of DNA's double helix. A geneticist might explain that DNA has been running a massive, billion-year data storage experiment, and its success is evident in the fact that the instructions to build a blue whale, a giant sequoia, or a human being are all stored within a microscopic package. A computer scientist would look at the same system and see a storage medium with unparalleled density. While the best modern solid-state drives can store a few terabytes of data per gram, DNA can theoretically store 215 petabytes, that's 215 million gigabytes, in a single gram. This isn't an incremental improvement. It's a difference of 5 orders of magnitude, a paradigm shift that could transform how we think about archiving data for the long journey to the stars. The application for space exploration is immediate and profound. A mission to another star system, or even a long-term colonial archive on Mars, would need to carry a massive amount of information: the complete scientific and cultural records of Earth, detailed engineering schematics for an entire civilization, agricultural databases, and the personal logs of the crew across generations. Storing this on traditional hard drives or tape would require tons of equipment, immense power to maintain, and would be susceptible to cosmic radiation that can slowly degrade digital media, flipping bits and corrupting files over time. DNA storage presents an elegant alternative. A single, small vial of synthetic DNA could hold all of it, and it wouldn't require constant energy to maintain its state. Just like the dinosaur DNA preserved in amber for millions of years, data encoded in DNA could remain stable for millennia if kept in a cool, dark, and dry environment, conditions easily found in the subsurface of Mars or in the shielded hold of a generation ship. Perhaps one of the most ingenious aspects of this biological model is its built-in error correction. Digital systems use complex algorithms to detect and fix errors, but they are not infallible. DNA, however, has been perfecting this art for eons. The molecule is double-stranded, meaning every piece of data is automatically backed up. Specialized repair enzymes constantly patrol the helix, proofreading the code and fixing mismatched bases, much like a spellchecker operating at the molecular level. This natural redundancy and repair mechanism directly inspires new approaches to safeguarding digital information. Computer scientists are developing error correction codes that mimic this biological process, creating data storage systems that are not only dense but also incredibly robust and self-repairing over time. This means an archive on a distant world could maintain its integrity against the relentless onslaught of cosmic rays and random decay, preserving humanity's legacy long after the devices we use today would have succumbed to entropy. This vision is already moving from the theoretical to the tangible in laboratories on Earth. Tech giants like Microsoft, in collaboration with research institutions such as the University of Washington, are running active DNA data storage initiatives. They have already successfully encoded and retrieved massive datasets, including entire books and video clips, in synthetic DNA. The process involves translating the binary code of digital files into the base pair code of DNA, for example, 00 might become A, 01 become G, and so on, then using a standard synthesizer to literally print the DNA sequence. To read the data back, they use a DNA sequencer and software to translate the bases back into binary. While the speed of writing and reading is currently too slow for everyday use, it is perfect for the cold storage of archives information that needs to be written once and stored safely for a very, very long time, exactly the use case for a time capsule sent to another world. This entire endeavor forces us to reflect on the very nature of permanence and security. Our current digital universe is incredibly fragile, built on formats that become obsolete within decades and hardware that physically degrades. A future archaeologist on another planet might unearth a modern hard drive and have no way to access its contents, but DNA is different. As long as there is life or an understanding of biology, the code of DNA will be readable. It is the ultimate future-proof format, encoding our most precious data in this universal language of biology ensures it will be accessible to any civilization advanced enough to understand the basic principles of genetics, making it the most secure and long-lasting time capsule we could possibly send into the cosmos. It represents a profound convergence of the biological and the digital, suggesting that the ultimate technology for preserving our future might be the same ancient molecule that has so faithfully preserved our past. So we arrive at a profound and unsettling crossroads, armed with nature's deepest mathematical secrets and the power to reshape worlds. We can now design a habitat that grows like a plant, coordinate robots with the swarm intelligence of ants, and shield ourselves with materials that heal like living tissue. But this incredible power forces us to ask a question we have never had to confront before. Do we, as a species, have the right to impose an Earth-derived blueprint onto pristine alien environments that have followed their own silent, evolutionary paths for billions of years? This is no longer just an engineering challenge. It is the ultimate ethical and philosophical frontier, where the cold logic of mathematics meets the warm, messy responsibility of cosmic stewardship. This dilemma is formally enshrined in the principle of planetary protection, a set of guidelines established by the International Committee on Space Research. At its heart, planetary protection is a form of interstellar bioethics. It's not about protecting our spacecraft from other worlds, it's about protecting other worlds from us. The core fear is twofold: forward contamination and backward contamination. Forward contamination is the risk that we might accidentally transport hardy Earth microbes, like the radiation-resistant Deinococcus radiodurans or the tenacious tardigrade, to another planet. If these stowaways were to survive the journey and find a foothold on, say, Mars or Europa, they could irrevocably contaminate that environment. Not only would this destroy our chance to ever discover a truly independent form of alien life, but it would also make us guilty of the most profound act of interplanetary imperialism, unintentionally seeding another world with our own biological baggage, effectively erasing its native history before we even had a chance to read it. The reverse scenario, backward contamination, sounds like the plot of a science fiction film, but is taken very seriously by agencies like NASA. This is the hypothetical risk that a sample returned from another world, perhaps from the subsurface ocean of Enceladus, might contain a biological agent that could be harmful to Earth's biosphere. While the probability is considered extremely low, the potential consequence is so catastrophic that it mandates an overwhelming precautionary principle. This is why samples from asteroids like Bennu and future samples from Mars will be met with maximum containment protocols, treated with the same level of caution as the most dangerous pathogens on Earth until they are proven safe. The precautionary principle dictates that in the face of scientific uncertainty and potential for severe harm, the burden of proof falls on those proposing an action to demonstrate it is safe, not on others to prove it is dangerous. It is a principle of humility, acknowledging the vastness of our ignorance. This leads to a fundamental tension in cosmic design philosophy. Should we aim for minimal impact or embrace our role as planetary transformers? The minimal impact approach, favored by many astrobiologists and conservation-minded scientists, argues that we should be like interplanetary visitors in a sacred cathedral, taking only pictures and leaving only footprints. This would mean designing missions that are hermetically sealed, using sterilized robots that tread lightly and leave no permanent mark. It prioritizes the preservation of other worlds as pristine scientific laboratories for study, not settlement. On the other end of the spectrum is the philosophy of terraforming and large-scale transformation, which views other planets as humanity's next home and a necessary outlet for our long-term survival. This school of thought asks if we have not just a right, but a moral imperative to use our knowledge to make barren worlds habitable, to create new branches of the human family tree among the stars. It envisions engineering on a planetary scale, redirecting comets to deliver water, releasing genetically engineered microbes to thicken atmospheres, and ultimately creating a second Genesis, a human-directed Genesis on another world. Current space policy is cautiously navigating this divide. The Artemis Accords, which guide the upcoming return to the Moon, include provisions for creating safety zones around sites of historical and scientific interest, a first step toward a kind of extraterrestrial environmental protection. But as private companies enter the arena with ambitions for resource extraction and tourism, the ethical framework is being stretched thin. Who gets to decide the fate of a world? Is it the scientists who wish to study it, the engineers who can transform it, the corporations that can profit from it, or all of humanity collectively? This isn't an abstract debate. It will define the soul of our future in space. Will we be careful archivists of the cosmos, or will we be its ambitious and perhaps reckless architects? The mathematical codes we have decoded from nature give us immense power, but they do not come with an instruction manual for ethics. That we must write for ourselves, understanding that every design choice we make for an alien environment is not just a technical decision, but a profound statement about who we are and what we value as a species. From the spiral of a galaxy to the spiral of a nautilus shell, from the collective wisdom of an ant colony to the quantum navigation of a migrating bird, we have journeyed through a universe not of random chaos, but of breathtaking mathematical order. We have seen how fractal geometry provides a universal blueprint for efficiency, how the golden ratio whispers of cosmic aesthetics, and how algorithmic growth and swarm intelligence offer a new paradigm for adaptive, resilient exploration. We have delved into the quantum mysteries harnessed by life itself and confronted the profound ethical responsibility that comes with wielding this ancient, universal toolkit. The message is clear and humbling. The solutions to our greatest extraterrestrial challenges are not always found in inventing something entirely new, but in learning to see the genius already written into the world around us, a deep code of cosmic design that has been billions of years in the making. This exploration suggests a truly awe-inspiring possibility, that the cosmos might share a common design language, a universal set of mathematical principles that govern everything from the formation of stars to the growth of a fern. We are not imposing an Earth-centric view on the universe. Rather, we are discovering that we are products of this universe, and the same logic that shaped our world likely shapes others. We are learning to listen to a harmony that has been playing since the dawn of time. It brings to mind the timeless words of Carl Sagan, who so beautifully captured this unity of knowledge. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. This journey of interstellar engineering is, in the grandest sense, the universe beginning to understand its own inherent patterns and potentials through us. Now, this future is not just for rocket scientists and biologists in isolated labs. It is an interdisciplinary frontier, and it invites all of us to participate. Whether your passion lies in coding, design, ecology, or ethics, there is a role to play in this great collaborative project. Think about the bio-inspired idea that most captured your imagination. Was it the notion of self-healing materials that repair themselves like skin, or the potential for symbiotic habitats that function like a living ecosystem? Perhaps it was the incredible promise of DNA data storage, safeguarding our legacy in the molecule of life itself. Whatever it is, that curiosity is the first step. Share it in the comments below. I am genuinely excited to read what resonates most with you and to continue this conversation. If this glimpse into a future shaped by nature's math has sparked your sense of wonder, be sure to subscribe and hit the bell so you don't miss our next exploration into futuristic technology. We have provided links in the description to dive deeper into the research from NAS, Institute for Advanced Concepts, and other pioneering organizations. The code is being cracked, the blueprints are being drawn, and the journey is just beginning. Thank you for watching, and remember, the next great breakthrough for humanity may not be found in a distant star system, but waiting to be discovered, decoded, and deployed from the incredible world